spectrum that was being observed. So Pauli proposed that instead of a two-body decay, actually the beta decay is three-body, the final state should be three-body, and the missing energy was actually carried away by the particle called the neutrino. So this offers a very nice way to explain the observed energy spectrum while maintain energy molecule conservation. Neutrinos come into three flavors. The electron neutrino is a type of neutrino that was participating in the weak charge current interaction associated with the electron. And likewise, we have the muon neutrino and the tau neutrino. On the other hand, these three flavored neutrinos, they do not have definite masses. So what that means is they are actually linear combination of three neutrino mass eigenstates, nu1, nu2, and nu3. And here just to give you a picture of what that composition sort of look like. All right. So given that neutrinos are produced and detected through the weak interaction, what that tells us is that it is a neutrinos that have definite flavors that are being produced or detected. But from quantum mechanics, we know that it is neutrinos that have definite masses that will propagate in a definite way a la the Schrödinger's equation. So here we have neutrino mass eigenstate 1, 2, 3. These are the states that propagate where electron neutrino, muon neutrino, and tau neutrinos, these are the states that participate in the weak interactions. And therefore, these are the states that get produced and detected. So this is a little bit like the classical mechanics problem some of the undergrads or even grad students are familiar with, where if I have a couple of oscillators, each of the object has a coordinates x1 and x2, and they are connected by a spring. You know x1 and x2 individually are not the normal modes, right? But what are the normal modes? Like either like this, or they move together. Very good. So this is very similar, to the. This is a very good analogy to the fact that the neutrino mass eigenstates do not coincide with their flavor eigenstates. All right. So suppose at the neutrino source, which could be the sun, or the nuclear reactor, or the accelerator, this is a neutrino of a definite flavor that being produced. So in the sun, we have the electron neutrinos that get produced. In the nuclear reactors, we have the electron antineutrinos that are produced. And at the accelerator, we have the muon neutrino that is produced. But when they propagate according to their mass eigenstate. So what that is telling you is, depending on where your detector is located, you may detect a different composition of the three flavors of neutrinos. Yes? All right. So once again, this is a very nice simulation where that shows you at the neutrino source, again, a definite flavor is being produced, and they propagate according to the mass eigenstate, and the detector, you may detect a different composition of the two flavor states. So again, this is a very easy quantum mechanic, or a very nice quantum mechanic problem to derive the oscillation probability. And I'm not going through the detail, but just to remind you that if I started out with neutrino of some flavor, say nu mu, and you want to ask what is the probability of neutrino of the electron flavor that is being detected some distance L away from your source, then the oscillation amplitude is determined by this mixing angle theta, which tells you how the two eigenstates are correlated. Right? So here is my nu1 and nu2, and they form their linear combination form the nu e and nu mu eigenstates, and this angle is theta. Right? So in this two flavor case, these two set of states are related by just one mixing angle theta. and then you can crank to the mass and work out the solutions to the Schrödinger's equations. This is your end result. So the oscillation amplitude depends on this angle theta, where the oscillation length depends on how far away the detector is and what is the mass square differences between these two mass eigenstates. All right. So this is the full result here. And once again, the oscillation length depends on the delta m squared, where the amplitude depends on sine squared 2 theta. And these are the parameters that the experiments are trying to measure. All right. So now we already observed neutrino oscillations. That tells you neutrino must have masses, right? Otherwise, delta m squared will be 0, and you will get infinite oscillation length, and therefore, if there's no mass, then you don't get oscillation. So you can work with that logic. Very good. All right. So of course, neutrinos are just 3 out of the many elementary particles that forms the building block of our universe. And so far, our knowledge is described by the so-called standard model, which is a gauge theory based on the group SU3 color plus SU2 left plus U1 hypercharge. And the particle contents are the 3 generations of quarks and leptons. So in addition to the 3 flavored neutrinos that we already see, there are also 3 charged leptons, and in addition, there are 6 quarks, and they are organized in terms of, into 3 generations, right? The SU3s, this describe the strong interactions, which contains 8 gluons. So these are the force carrier, the force carrier of these strong interactions, which bonds the quarks inside neutrons and protons. The SU2 plus U1 part of the gauge interaction is describe the electromagnetic and weak interactions. So there's corresponding W and Z bosons in addition to photons. So this is the full building block of our universe, except that there's also the Higgs, which was recently discovered, and that I'm not showing on this block. All right, so in the very early universe, it was dominated by the particles, and of course the interactions and the properties of these particles would determine the subsequent evolution of our universe. So all the fermions that we've seen have both the left-handed and right-handed partners.
I have a question.
Yes.
This representation, this imaging of the fermions and so on is also standard already?
What do you mean?
The picture.
The picture? Which one? These are the 2. These are rather standard, and they come in this size, I believe. And they are very fluffy. Yes, they are standard. Even the neutrinos, also neutrinos, and the Higgs, they all exist. All right, so all particles come with both left-handed and right-handed partners. However, only the left-handed neutrinos have been observed. So here, immediately, you already see a disparity between neutrinos and other elementary fermions. And these facts will become important when we talk about neutrino masses. So all these fermions, they acquire their masses through the so-called Yukawa interactions. Basically, the left-handed fermion and right-handed fermion, they mix and interact with the vacuum excitation value of the Higgs particle. And effectively, this gives you a mass. Okay? But we just saw that there are no right-handed neutrinos in the standard model. And therefore, left-handed neutrinos cannot interact with the Higgs, and therefore, neutrinos stay massless. Or in other words, standard model predicts massless neutrinos due to the absence of the right-handed neutrinos. The Higgs particle was discovered in 2012, and that, of course, led to the Nobel Prize to Engler and the Higgs. And this is our new periodic table of the particle physics, which in addition to the 6 quarks and 6 leptons and the 4 carriers, now we also have to add the Higgs. Okay. And again, we have 3 generations of quarks and leptons. And just remember that as we move up the generation, the particles become more and more massive. Even though the quantum number, if you just look at the standard model quantum numbers across the generations, they look exactly the same. All right? But as you move up the generations later, the particles become massier and massier. And again, just remind yourself, all the fermions come in both left-handed and right-handed partners, except for the neutrinos. All right? So now if I put all the elementary particles on the standard model on this plot, this is what their masses are situated. And just to remind you, here I plotted their masses on the log scale. So immediately you already see there's a huge disparity among all the fermion masses. They range from electron mass, which is about 0.5 MeV, all the way to the top quark mass, which is about 170 GeV. So this is a huge 6 orders of magnitude differences among the elementary fermions. And to give you some perspective, the neutron mass or proton mass is about 1 GeV, sitting right here. Oops. Oh, sorry. Even though we know the Higgs particle is responsible for generating all fermion masses, but it doesn't really explain this observed mass spectrum. Right? In the standard model, all the masses are given by undetermined Yukawa coupling constants. So the Yukawa interaction that I showed you before was an undetermined strength, namely the Yukawa couplings. And with this large set of undetermined Yukawa coupling constants in the standard model, this is how the charged fermion masses are, obtained. So once again, standard model predict massless neutrinos because there are no right-handed neutrinos. In addition to this puzzle, namely this huge disparity among charged fermion masses, there's another mystery in the standard model, and that concerns the fact that the mass eigenstates and the flavor eigenstate do not coincide. So I already alluded to a bit in the neutrino sector, but such mismatch also occur in the quark sector. So again, the quarks in the flavor states, which I drew here, these are the states that participate in the charge current weak interactions mediated by the W bosons. However, these weak interaction eigenstates do not have definite masses. So once again, just like this theta angle that we introduced earlier, that tells us how you rotate from one set of eigenstates to another. Here, our weak eigenstates in the quark sector and the mass eigenstates are related through a unitary transformation. Right? So this unitary transformation is a so-called CK matrix, which contains 3 mixing angles and 1 complex phase. All right. So again, the weak eigenstates is a mixture, or are the mixtures of mass eigenstates. And this this phenomena led to the discovery led to the Nobel Prize in 2008 to KNM. So how about the neutrinos in the standard model? Given that standard model predict massless neutrinos, what that means is all the 3 mass eigenstates are 0. They are degenerate. So what do you learn from linear algebra? It's for the series. If you have 3 eigenvalues to be the same, what that tells you is you have the freedom to choose the eigenstates so that the mass eigenstates and flavor eigenstates coincide. Right? So this is a spatial property when you have the eigenvalues be degenerate. So what this is telling us is that there appear to exist some accidental symmetries in the standard model that protect certain processes that go across the family lines. Alright? And these accidental symmetries correspond to the individual Lepton flavor number, Le, L mu, and L tau. And with these accidental symmetries, no processes that come across the family lines in the lepton sector can occur. And therefore, there's no neutrino oscillation. Various charged lepton flavor violation decays are forbidden. So you don't have mu-E conversion. You don't have the radiative charged lepton decays. And given that individual lepton flavor numbers are conserved, that tells you their sum must be conserved as well. So the total lepton number is also conserved in the standard model. Right. And of course, we observe neutrino oscillation that tells you these selection rules, these accidental symmetries are broken. Alright, so neutrino oscillation now is observed, and the next obvious question is whether we can also observe flavor violation in the charged lepton sectors. And there's actually there's a lot of experimental efforts trying to look for this type of rare processes like mu-E conversion. And another question is whether the total lepton number is conserved, given that individual lepton flavor numbers are no longer the symmetries. And this, of course, is closely related to a fundamental property of the neutrino, namely whether neutrinos are their own antiparticles, namely whether neutrinos are Majorana fermions. Alright, so if the neutrinos have mass, which we know they do, then similar to the quark sector, there can be mismatch between their mass eigenstates and weak eigenstates. So again, what I show here, these are the three flavor eigenstates, mu-E, mu-mu, and mu-tau. They are linear combination of the three mass eigenstates, mu1, mu2, and mu3. These two set of eigenstates are related by the so-called PMNS matrix, which includes three mixing angles. But depending on the property of the neutrinos, namely whether neutrinos are Dirac or Majorana fermions, there exists one phase for the Dirac case and three phases for the Majorana case. All right. Any questions? Okay. All right. So where do we stand now as far as the experimental situation goes? If we put all the known data together, these are the two pictures that are consistent with the current data. On the left, this is called the normal hierarchy, where the nu3 mass eigenstates is the heaviest one, and nu2 and nu1 are the lighter mass eigenstates. This square mass difference here is driving the atmospheric neutrino oscillation, and experimentally we know this is on the order of 10 to the minus 3 electron volt square, where the mass square difference here between nu1 and nu2, this is driving the solar neutrino oscillation, and it is on the order of around 10 to the minus 5 electron volt square. And just to clarify, the nu3, nu2, nu1, these mass eigenstates are defined in terms of their flavor composition of mu-E, mu-mu, and mu-tau. Alright, so different colors indicate here. This dark purple indicates the composition of mu-tau. This light blue indicates the composition of mu-mu. And this pink color indicates the composition of mu-E. Right. So this picture on the left, normal hierarchy, agrees with the current experimental data. But so is the inverted hierarchy picture, where the nu2 and nu1 mass eigenstates are the heavier ones, and nu3 mass eigenstates is the lightest one. Right, so here again, just to show you, now we have nu1, nu2, nu3, which are linear combination of nu e, nu d, nu tau, and that rotation, how you map from one set of eigenstates to another are determined by this three mixing angle, theta 1, 2, theta 2, 3, and theta 1, 3. And experimentally, we know theta 2, 3 is from atmospheric oscillation. This is very close to maximum, but it is not exactly maximal. And I'll come back to this point later, where in the solar sector, we can measure theta 1, 2. This is roughly 33 degrees. And the 1, 3 mixing angle, this was discovered just a few years ago at the reactor experiment. This is on the order of 9 degrees. All right. So even though we already made a lot of progress over the last maybe 2 decades in knowing about the neutrino properties, there are still a lot of fundamental properties of the neutrinos that we do not know. So are neutrinos their own antiparticles? Right? This is a very deep question, and I think personally this is the most important question that needs to be addressed. And in the more technical terms, whether neutrinos are Majorana or Dirac fermions. Is there CP violation in the lepton sector? And this, of course, is very closely related to the question, why are there more matter than antimatter? And there's a very nice mechanism called leptogenesis, which is tightly connected to the neutrino property. So we will see more of that later. What is the absolute mass scale of the neutrinos? All right. Given that, experimentally, through the oscillation experiment, we can only measure the 2 delta m squared, because that's what enter into the oscillation formula, right? That's what determines the oscillation length. But how about the absolute masses of nu1, nu2, and nu3? So far, we still don't know. What is the mass ordering? Namely, whether the inverted hierarchy picture is correct or the normal hierarchy picture is correct, as I showed you on the previous slides. Are there more than 3 neutrinos? Are there the so-called stereo neutrinos, which may be relevant for a lot of experimental anomalies that we heard about? And how about the precision? Right? We just saw the theta 2, 3 angle from the experiment is large, but it is not exactly maximum. And if, say, the angle turns out to be exactly 45 degrees, that then give you very strong indication that there might be an underlying discrete symmetry of the type of Z2 that is at work, right? So the precision of this is important, because if it, the 3 situation, whether theta 2, 3 is exactly maximal, or whether it's smaller than 45 or larger, this may tell us something about the underlying symmetry that gives rise to this mixing pattern. And also, does a Higgs particle give masses to the neutrinos? Because neutrinos are special, they are neutral, right? So that open up additional ways that they can acquire their masses. So again, this is also an unknown question. The answer to this question is still unknown. There are a suite of current and upcoming experiments trying to address these puzzles. And theoretically, in order to understand these properties, you do need to understand the quantum physics. Right? So that's what we'll be doing. So if I now concentrate on the neutrinos, here broadly speaking, there are 2 theoretical questions. One is concerning the fact that the neutrino masses are much smaller compared to the charged fermion masses. So earlier I just showed you this part, which are the charged fermion masses. But now if I just put in the neutrino masses, now immediately you see this disparity is coming across not 6 orders of magnitude, but 12 orders of magnitude. Right? So how do you explain why neutrinos are so much lighter compared to the charged fermions? And the next question concerns the flavor structure. If you put the CKM matrix, what you get is this near identity matrix, namely quarks, they don't really mix that much, right? So it's dominantly, to the leading order is identity matrix. On the other hand, if you look at the lepton mixing, the picture is very different because it's based on the values I show you. All the 3 mixing angles are rather large, right? At least 2 of them are rather large, and the smallest one, theta 1-3, is on the order of the Cabibel angle. Right, so these 2 pictures are, they look rather different. And in other words, if I just look at the mixture of the weak eigenstates versus mass eigenstates, this is basically stating the same thing. So how do we reconcile these 2 drastically different flavor structures in a fully consistent theory? Alright, so far, we don't know. And furthermore, what is the underlying dynamics that can give rise to such pattern? Alright, so again, just to remind you, this is one great puzzle in the standard model, namely the fermion masses and hierarchy. This require, in the standard model, many free parameters in the Yukawa sector. And by many, that means 22. That's huge. Whether there's any way to reduce that, namely, where do fermion mass hierarchy, flavor mixing, and CP validation come from? Is there any simpler organization principle that can cause us such patterns? And where do neutrinos get their masses? Namely, is there a Higgs or something else that contribute to the neutrino masses? And another related question is, we know the universe now is dominated by matter, right? But given that matter and antimatter behave in the same way, you would expect the universe, when it was first created, there was equal amount of matter and antimatter. So what happened to all the antimatter? Where do they go? And it turns out neutrinos may play a very important role in generating this matter-antimatter symmetry, and that requires the existence of lepton CP violation. So we'll look at this more on Wednesday. All right. So I'm going into more technical aspect now. Right. So when I show you this table, so don't worry about the detail. But what I show here, this is the current, probably not the most up to date, but close. Close to latest 3 neutrino global analysis. So what global analysis means is they combine all the available experimental data and ask what would be the best fit in terms of the set of experimental parameters that can fit the most, all the data well. And just to draw your attention, the key point to take away is that now we have evidence of a sizable theta 1-3 on the order of 9 degrees. There's also a hint of the atmospheric mixing angle theta 2-3 away from 45 degrees. And I think most interestingly is that from the global fit, now we already can extract certain expectation of the Dirac CP phase, delta. All right? Even though statistically it is not significant, but nevertheless, I think this is interesting. There's still no very clear preference for the mass hierarchy. And of course, we still don't know whether neutrinos are Majorana or Dirac. And of course, we don't know whether, the stereo neutrinos, that's still the anomaly. There still exists a lot of experimental anomalies in the reactive sector, and we don't know whether stereo neutrinos exist or not. Beyond the oscillation experiments, we can also extract, various properties of the neutrinos. For example, from the endpoint kinematic of the tritium beta decay, we can obtain a bound on the epsilon mass scale of the neutrinos. So this is currently on the order of 2 electron volts, and Cat3 will increase the sensitivity by a factor of 10. So please correct me if there's more refined statements about this. We also have neutrino-less double beta decay experiments that can bound this combination of the oscillation parameters. So this is a combination of the absolute masses of each mass eigenstate multiplying the PM and S matrix elements. All right, so this combination is bounded by, current bound is roughly 0.1 to 0.3 electron volts. And again, there is certain uncertainty because of the nuclear matrix elements. From cosmology, we also have the bound on the sum of the absolute masses of the neutrinos. It's on the order of 0.2 electron volt. And there's also the limit on the number of effective degrees of freedom, which is very close to 3. So the deviation, the allowed deviation is rather small. Of course, if the stereo neutrinos are fully thermalized in the early universe, then this would strongly disfavor the scenario with the stereo neutrinos. Alright, so just to remind you again, these are the 2 theoretical problems that we are trying to address. And I'm just going to look at what are the possible new physics that can address these 2 aspects of the questions, and what these different theory possibilities they differ, and what new predictions they may lead to. So first, consider the scale of the neutrino mass generation. So why neutrino masses are so small. And then come down to the question, what precisely is the operator that generates the neutrino masses? In different type of scenarios, neutrino could either be Majoranas or Dirac. So what that means is both Majorana and Dirac scenarios can be accommodated. So there exist models that can explain both, even though I think due to the theoretical prejudice, more focus has been played on the Majorana neutrinos. All these mechanisms also differ by the scale of the operator. So namely, the scale of the new physics could differ. Okay? And they also differ by the suppression mechanism, namely what suppress the neutrino masses. So I'm just going to show you a few examples. Alright, so if you believe, and you should, that there's new physics beyond the standard model, what that tells you is that standard model at best is an effective low energy theory, right? So if you take that attitude, then what that tells you is there should be new physics effects that you need to include. And they show up through these higher dimensional operators. And one already told us back in the late 70s that one of those new higher dimensional operators that can characterize the new physics effects can already give you the neutrino masses. And that is famous dimension 5 Weber operator that coupled to Higgses to 2 Lepton doublets. Alright, so this is HHLL, and INJ here just indicate the generation indices. Lambda here is some coupling constants, and M here is the scale of the new physics. Alright. So if you put in the observed delta M squared atmospheric value and take that as the mass scale of the neutrino, effective neutrino mass, so this come out to be around 0.1 electron volt. And yes, and we know the Higgs wave is 100 GeV-ish. And if you assume that the coupling constant has to assume a natural value, and by natural I mean order 1, yes, then it turns out that this new physics scale, which is needed to generate an effective neutrino mass scale of 0.1 electron volts, turns out to be 10 to the 14 GeV. So this is a really, really high scale, which is very close to the grand unification scale. All right. And given that this operator violates a total lepton number, because this is delta L equals to 2 operators, here I have 2 leptons, neutrinos are Majorana fermions. So this new physics scale 10 to the 14 GeV is very close to the grain unification scale. What this is telling you is that, or what this indicates, is that grain unification or grain unified models can actually not naturally accommodate small neutrino masses. And tomorrow, Michael would talk more about this in his discussion of neutrinos in grain unification and string theories. All right. So this is the Weinberg operator I showed you before. 2 leptons coupled to 2 Higgses. And here, this is a block that contains all the new physics effects, new particles that can help you to UV complete this operator, higher dimensional operator. So you can ask, what are the possibilities that can go into this block, right? If you use a very fashionable language, the Portal, which is used a lot in the dark matter community, there are in total 3 possible portals. One is the right-handed neutrinos, which is a pure singlet under the standard model gauge group. Right? It is a fermion. It doesn't carry any quantum number under the standard model gauge group, and it can be the mediator of this higher dimensional operator. So this is the Feynman diagrams, or the so-called type 1 seesaw mechanism, when this Weinberg operator is UV completed by a right-handed neutrino. But this is not the only possibility. There is so-called the type 2 seesaw mechanism, where the Weinberg operator is UV completed by a SU2 triplet Higgs. All right, so that's a triplet Higgs, triplet under the SU2L, and it carries 2 units of the hybrid charge. It is a scalar field, and this is a corresponding diagram. So this is the so-called type 2 seesaw mechanism. In addition, if you have a triplet fermions, and again, by triplet I mean it is triplet under the SU2 weak gauge group, and it carries 0 hybrid charge, this is the third possible way to UV complete the Weinberg operator. All right, so sigma R here is a triplet fermion. And if this is the case, this is called the type 3 seesaw mechanism. All right, so since Michael will concentrate on the high scale scenario, I'll just spend a couple minutes discuss the possibility where the seesaw mechanism can be implemented at the TeV scale. Because now LHC is running, and you may wonder whether LHC can contribute to the searches or to help us learn about the neutrino sector. And you will see the answer depends on the scenarios. So for type 1 seesaw mechanism, once again, type 1 seesaw is a seesaw mechanism that is mediated by a singular fermion, right-handed neutrino. If you were to lower the new physics scale from 10 to the 14 GeV, in which case the corresponding coupling constant is order 1, but if you were to lower it down to a TeV range, then correspondingly, you need to lower the coupling constant. Yes? All right. So if I take, yes. So if you were lower this, yes, the new physics scale, meaning the right-handed neutrino mass in this case, down to TeV, you would need to reduce the corresponding coupling constant to the order of 10 to the minus 6. And you may say this is rather unnatural, right? Maybe, maybe not. But some people also take the attitude that we do have such unnaturally small coupling constant in the standard model, namely the electron Yukawa. It is also on the order of 10 to the minus 6. So if you think that's acceptable, then this may be an acceptable scenario. But let's just take this and see how far we can go. All right. So given that the right-handed neutrinos do not carry any standard model gauge quantum numbers, the only way you can produce them is through the mixing between the active and the stereo state, right? Because another way to produce them is by the Yukawa interaction. But given that the Yukawa coupling is so small, this option is not really relevant. So right-handed neutrino production in this case is due to gauge interaction, but the gauge interaction is possible because it's through the heavy and light mixing. And the heavy and light mixing is given by the ratio of the Dirac mass to the right-handed neutrino mass, and this turns out to be 10 to the minus 6, which is really small, right? And it was actually analyzed and concluded that in order to have observable effects at the collider, this require a active and heavy and light mixing on the order that is greater than 0.01. So what this is telling you is that, if this right-handed neutrino is really the state that contribute to the neutrino mass generation, then there's no hope of discovering it at the collider. So when the experimentalists, try to make claim that, we place a bound on the right-handed neutrino or we discover right-handed neutrino, we have to really keep in mind what is a relevant parameter space for the neutrino mass generation. All right. So for type 2 CISO, the situation changes. Now you have a triplet Higgs, which carry the weak gauge quantum number. And here, I'm just going to rush through because I'm too slow. Given that this triplet Higgs, it is a SU2 triplet, one very special property it has is that it carries a doubly charged component. So a very clean signature is this doubly charged components in the triplet Higgs decay into same-side dileptons. This is a rather clean signature, and there are searches at the collider experiment placing the bound on the limits of this doubly charged guy. For type 3, here you have the triplet of fermions, a triplet under SU2, and the signature in that scenario is the observed displaced vertex observed on the order of millimeter scale due to the TeV scale triplet decay. All right. There's also the so-called inverse CISO, and I know Michael will talk more about the CISO mechanism, but here just to add that in the regular CISO you have the left-handed neutrino, which is a guy that we already have in the standard model. The right-handed neutrino, which is what you add, the singlet that we saw in the type 1 CISO. But you can also add one more singlet, right? And that leads to this mass matrix. If you work out the mass, what turns out is that this is rather complicated than the usual CISO formula. But what you find is that with all this, the scale of this new scalar degrees of freedom on the order of TeV, and with the other guy, this MS, the mass, roughly the mass of this additional singlet on the order of 0.1 keV, you can naturally generate an effective neutrino mass on the order of 0.1 electron volt. All right, so here are just a few signatures that where the model includes the new particles and various collider signatures you may have, except for the type 1 CISO. But you could also have, expand your gauge interactions to be, say, the Lebesgue symmetric, to be Lebesgue symmetric. And in that case, you also have the additional gauge boson, say the WR. With our parity violation in minimal supersymmetry standard model, you can also generate the neutrino mass. And here I have a example here. This is a bilinear R parity violation operator, which can lead to the neutrino mass generation through this diagram here. Right? And given that this is the same operator that leads to the neutralino decay, now you can have a correlation between the mixing angle in the neutrino sector versus the ratio of the neutrino decays into different final state channels. All right. So what if neutrinos are direct fermions? So far, I talked about the UV completion of the Weber operator, which leads to Majorana fermions, right? Because the Weber operator, again, it violates the lepton number by 2 units. But what if neutrinos are direct? Namely, what if the total lepton number, or what if there's no delta L equals to 2 violation? I have to be careful with that. All right. So there are 2 ways you can naturally generate neutrino masses of the Dirac type. One is through SUSY breaking. All right, and the idea is that before supersymmetry is broken, the Dirac neutrino masses as well as the Weber operators, those are absent. And after SUSY is broken, realistic effective Dirac neutrino masses can be generated. All right, and given that this generation is induced by SUSY breaking, the size of the neutrino Yukawa coupling constant must be related to the order parameters that determine the SUSY breaking, and that turns out to be the gravitational mass. Right, so this mechanism, the effective neutrino Yukawa coupling, is given by this ratio, which is the SUSY breaking order parameter, namely the gravitational mass, to the Planck scale. And if you have a scenario such as the anomaly mediated SUSY breaking, where the gravitational mass is on the order of 100 TeV-ish, then this ratio will give you roughly the correct order of magnitude for the Dirac Yukawa coupling, and therefore naturally small Dirac mass. And this is very similar to the so-called Giudice-Masiero mechanism for the generation of the mu term. Namely, before SUSY is broken, mu term is absent in the superpotential. But once SUSY is breaking, that effect gets mediated to the visitor sector and effectively generating a mu term, which is on the order of m3 So it's very similar. And of course, the question is whether you have any symmetry reason that kills all these operators before SUSY is broken, right? Because always what it's talking about here, this is just a mechanism. But to realize this, you do need a model. You do need some symmetry that realize this. Yes.
Is that formula from Akani Hamed et al. Is that independent of both the supersymmetry breaking mechanism and the supersymmetry breaking mediation mechanism?
This is, let me see. This depends on the mediation mechanism.
Yes.
Right? This is.
But it's always predicted to be non-zero, or?
What do you mean?
The neutrino mass. I mean, are you saying that if there is supersymmetry, if there is an MSSM, and
I see what you mean, right?
There's
right.
guaranteed to be neutrino mass. Is that the same?
No.
No, because all of this has to work out, the symmetry protection. So, in a realistic model, that doesn't always happen. You have to work to make that happen. Right? So that's what I said, this is just a mechanism. But in the realization, you need to provide a symmetry reason why certain operators are forbidden and why certain operators get generated and why they get generated with this order of magnitude. Yeah? And that's what this is. So we do have, models, existent proof that mechanism can be implemented, and that's based on a discrete R symmetry. And so, you have the symmetry reason why the Dirac and Weber operators are forbidden before the SUSY breaking, and why once SUSY is broken, the neutrino mass generation, why the SUSY breaking effect fits in and give you a neutrino mass on this order, why it appears at this order already, and that's controlled by the R charges of the fields. All right. But without going into more detail, the bottom line, the key features of this model is that delta L equals to 2 operators are forbidden to all orders. So they don't get regenerated at higher order, which is Nice. And therefore, there's no neutrino-less double beta decay. But that doesn't mean that there's no lepton number violation. That's why I say I have to be careful. It is only delta L equals to 2 operators are forbidden. But you still could have lepton number violation. And in our example, that violation actually appeared at delta L equals to 4. So again, all of these are controlled by symmetries. You don't have, freedom to change it. This just follows. So this delta L equals to 4 operators, which correspond to this new R to the 4th power operator term in the model. This is allowed, and this leads to new lepton number violation process, which is neutrino-less quadruple beta decay. So basically, just stitch together 2 neutrino-less double beta decay diagrams. That's neutrino-less quadruple beta decay. And I don't know whether there's any. I know one of the experiments actually tried to place the limits on it very recently. Of course, that may not be so significant statistically. All right. So in this model, mu term is naturally small. We can also forbid the dangerous proton decay operators. And if you want to invade this to allow for R parity violating operators, this could also provide a way where various the size of the RPV operators can be explained by the symmetry. All right, so I can skip that. All right, so now I come to the question concerning the flavor structure. And generally, there are 2 approaches. One is so-called anarchy. So basically, this is the approach that assumes that whatever value that you call out coupling path or neutrino masses and mixings are, these are just due to some, these are a little bit like landscape idea, right? They just assume the values they have. There's no underlying reason, like showing the dice. Another approach is to assume that there is an underlying symmetry whose dynamics control or give rise to the observed mass hierarchy and mixing pattern. All right, so I'm just going to look at these 2 possible approaches. So again, the anarchy idea is to assume that there are no parametrically small numbers, and the observed large mixing angles and near mass degeneracy, these are statistical results. These arise from statistics. So here, just to show you one example, is by Degove and Hitoshi Murayama. This is their original idea. Whereas you can see, this is the axis is the mixing angle, and you can see the parameter space allowed a large mixing is actually much larger. So it's statistically preferred. Even though at this level it looks rather random, but some of the UV theory can actually mimic, or the predictions from the UV theory can actually mimic the predictions from the anarchy. So one example is the warp electron dimensions, where you have the older one coupling constants, and the mass hierarchy and mixings are due to the overlap of the wave function, right? Because of the exponential factor that appear in describing the wave function profile. Now you can arrive at a very hierarchical mass hierarchy and mixing patterns, all with older one coupling constant. Right? Another type of UV theory whose prediction can mimic this anarchy prediction is the heterotic string theory. And I believe we will hear more maybe tomorrow from Michael. And basically what they found is that if you are starting from string theory, in the low energy spectrum, you actually get not only just one bracketed neutrino, like what I showed you before, that you be completely Weber operator, but you get order 100. Right, so this is what Sao and Michael and collaborators found more than 10 years ago. And if you remember that back of envelope calculation we did, we said in order to get light enough neutrino mass, this high energy scale has to be 10 to the 14 GeV. And for students who are familiar with square unification, you may say, aha, that's actually not exactly the Gauss scale, right? The Gauss scale is 10 to the 16 GeV, and there's a 2 orders of magnitude difference. Is that really natural, or you need to still do some tuning? What Saul and Michael and collaborators found is that in the presence of these order 100 right-handed neutrinos, you can actually naturally, bridge that gap. Because now, just in addition to one diagram, you actually you have not only one diagram, but you have some order 100 diagrams that contribute to the Weber operator, right? So that naturally bridge this gap between 10 to 16 GeV and 10 to the 14 GeV. But back to statistics. So in this type of string construction, where you have a lot of large number of right-handed neutrinos, their predictions for the mixing parameters can actually mimic the anarchic scenario. So this is an analysis done by Josh Tran and Claims back in 2012, where they look at the statistical prediction for the mixing angles with 3 right-handed neutrinos, 10 right-handed neutrinos, 30 right-handed neutrinos, and 100 right-handed neutrinos. So what you discover is that as I move up the number of right-handed neutrinos, the prediction actually pick toward large value for the mixing angle. Right, so this is one example of how a UV theory prediction can mimic that of enthalpy. All right, but personally, the approach that I would like to prescribe is a symmetry. Namely, I think it's nicer if there is an underlying symmetry that can give rise to the observed mixing pattern. And here I'm going to talk about 2 types of symmetries and what do they get us, right? So one type of symmetry is strain unified, it is a Gauss symmetry, which we will hear more tomorrow. But basically, due to the Gauss symmetries, now you have the relationships between the quarks and leptons. Right? That's the whole idea of strain unification. But another symmetry that I'll be concentrating on through the rest of my talk is a family symmetry. So basically, if you think about it, remember this standard model periodic table. All the 3 generations of fermions, they have exactly the same quantum numbers, except their masses. But if you want to understand how the mixing patterns come about, how the mass hierarchy come about, and remember, mixing pattern and mass hierarchy, this involves all the 3 generations, right? So it is natural to expect that there's a symmetry that acts horizontally among the 3 generations. You need certain quantum numbers to distinguish the 3 generations. So family symmetries give you relationship between electron family, muon family, and tau family. Right, so again, I think there's a better picture. Here you have the Gauss symmetry that relates the quarks and the leptons, where the family symmetry acts horizontally, which relate the 3 generations. Right? And what do we want symmetries? Because symmetry gives you relations among parameters, and therefore that leads to reduction in the number of fundamental parameters. And therefore, they could give you experimentally testable correlations among various physical observables. And therefore, that would be a way that experiments can help us to distinguish different classes of models, for example. All right. So what type of symmetries do we need, right? And of course, will be suggested by the data. So if you take the neutrino oscillation data, and in particular, the fact that the mixing angles are large, what they suggest is that the underlying family symmetry likely would be a discrete symmetry. Right? And in this framework, of combining just symmetry and family symmetry, they of course have a lot of work that has been done, starting from the quark sector that resort to continuous symmetry, because continuous family symmetries, because the quark mixings are small, and all the way to the recent efforts, a lot of efforts, that construct models based on discrete family symmetries. And we have a lot of local experts here who have worked on a lot and with various discrete symmetries that I listed here. And I believe we will have theory talks, which may theory seminars, which may touch upon some of these aspects here. All right. So just to give you one example of the discrete symmetry. And before that, I want to talk about why the discrete symmetries are motivated. Especially, there is a symmetry group called A4, which has drawn a lot of attention after the discovery of large neutrino mixing angles. So the so-called tribimaximal neutrino mixing pattern. So this tribimaximal neutrino mixing pattern is a mixing pattern of this form. And again, this is just one example. This is not, not the theory, but just one example to show the point. So the TBM mixing pattern is of this form. Basically, it tells you the new 3 mass eigenstates has equal composition of nu mu and nu tau, where the new 2 mass eigenstates has equal composition of nu e, nu mu, and nu tau, and the new 1 mass eigenstates has 2/3 of nu e, 1/6 of nu mu, and 1/6 of nu tau. And what this mixing pattern predicts is the fact that the atmospheric mixing angle is exactly maximum. And you can sort of see this because if you interchange this second row and third row, everything is the same, right? It's mutual, sort of mutual symmetry. It also predicts a solar mixing angle in terms of sine squared theta solar. This is equal to 1/3. So it's a very definite prediction. This mixing pattern also predicts a theta 1/3 value to be 0. And of course, immediately you jump up and say that's of course ruled out, right? Because earlier we saw theta 1/3 is 90 degrees. So this mixing pattern works really well, drew a lot of attention before the theta 1/3 discovery. And the reason is, if you look at these pattern values, they actually agree quite well with the global fit from the experiments, except for theta 1/3. And the approach is that this TBM mixing pattern, which could come from some underlying symmetry, I will show you on my next slides. These are just your leading order prediction. And of course, going beyond leading order, there are various corrections that you need to take into account. Right, so some of those corrections may be coming from the charged Lepton sector, and there are also additional corrections that are due to the kinematic terms that I will show you. All right. So one possible discrete symmetry that can give you this TBM tribimaximal mixing pattern is based on A4. So A4 describes even permutation of 4 objects. It's a nice group theory problem to work out. It has two generators. One generator is a reordering of 1, 2, 3, 4 into 2, 3, 1, 4. So this is even permutations of 2 objects. And the other generator is a reordering of 1, 2, 3, 4 into 4, 3, 2, 1. And geometrically, this is a group that leave a tetrahedron invariant with respect to rotations about these 2 axes. Right, so this generator actually corresponds to the rotations about this axis of 120 degrees. Right, that leaves this tetrahedron invariant. Where the second generator here, this generate rotations about this rotation axis, by 180 degrees. And once again, it should be easy to see that the 180 degrees rotation about this axis leaves this tetrahedron invariant. So it's a geometrical interpretation. And this is actually the group that can lead to the TBM mixing pattern. All right. So just that with the symmetry that leads to experimentally testable correlations among various physical observables. There could be, correlations among mixing angles and CP phase together with mass hierarchies, and there's also predictions or correlations with neutrinoless double beta decay, and also various charge lepton flavor violation. Right. So there's of course a suite of experiments trying to probe various of these observables. And I think one crucial thing is we do need a precision in order to test these correlations. And therefore, that's where the neutrino cross-section become important. Because you do need those cross-section in order to be able to get the desired precisions that need. So we may hear more from our experimental lectures on this. All right, so again, all right. So so one possible correlations among the mixing parameters is given by, so this is one example, where you have a theta 1-3. So this is actually maybe I shouldn't see that. Right, so just give you one example where I combine a SU5 grain unified group, grain unified symmetry, with a double covering of the A4 group I show you. And again, don't worry about the technical details, but the takeaway message is that in total there are 9 parameters in the Yukawa sector only that accommodate all the 22 physical observables. Alright, so basically what happened is you started out with a group where the family symmetry is exact. This family symmetry gets broken down in the neutrino sectors into some subgroup. Yes. Where it gets broken down in the charged lepton sector into a different subgroup. And given the mismatch between these two symmetry breaking patterns, that leads to the observed PM-ness matrix, for example. Right, so because of the symmetries, the number of parameters get drastically reduced, and in other words, you get correlations among the physical parameters. And 2 examples of such correlation. One is the 1-3 mixing angle in the neutrino sector, which is related to the Kabibel angle in the quark sector. So this is a result that follows from the grain unified theory that relates quarks to leptons. Yes. And I should mention that this factor of 3 divided by root 2, you don't have any free parameters to adjust this relation. These 2 factors are the group theoretical Clebsch-Golden coefficients of SU5 and this discrete symmetry group. And therefore, it is actually a very robust prediction because there's no free parameters that allows you to adjust this relation. And this turns out to be 3 degrees. So, of course, the model is ruled out. But this is a very nice model because you can rule it out, right? Good. Another correlation is between the solar mixing angle in the neutrino sector together with theta Kabibel angle and the Dirac CP phase in the neutrino sector. All right, so this factor that I indicate tangent square theta solar TBM, this is 1/2 because of the symmetry of the model. So again, this provides a way to test this framework. That is based on TBM mixing patterns. And of course, that is just one example, and there are other type of relations that coming out of different theoretical framework. So, for example, if instead of a TBM mixing pattern that you have, you may have the so-called bimaximal mixing pattern. And in that case, the correlation between the mixing angles are different. So this is theta 2-3 in the quark sector, which is really small, plus theta 2-3 in the lepton sector, and they add up to be roughly 45 degrees. So this is drastically different than the sum rule we have if you were to start with TBM mixing. So again, by measuring the leptonic mixing parameters to the precisions to the quark sector that we have, we may be able to distinguish these different type of scenarios. So I think that's a take-home message rather than the technical details here. Good. All right. So one possible, maybe I should mention this. Right. So this is another example of the correlations, where this is in the framework of the A4 I described earlier, but considering different symmetry breaking patterns. And that tells you the correlation between theta 1,3 and theta 2,3 for different A4 symmetry breaking pattern for normal hierarchy versus inverted hierarchy. So immediately what you see is that if theta 2,3 is not maximum, then that basically kills off the inverted hierarchy scenario because there's just no low parameter space there. And likewise, there's very strong, so similarly, there's very strong correlation between theta 1,3 and the amount of theta 2,3 deviating away from maximum for the normal hierarchy scenario. All right. So of course, this TBM mixing pattern, which can come out of a A4 symmetry, for example, is just the leading order prediction. And in addition to these leading order predictions, there exist corrections that must be properly taken into account. And one such corrections are those that are added to the kinetic terms. So this actually, I think, rather generic in models based on discrete symmetries. And the reason for that is that, again, for experts in the audience, the reason for this is that the flavon fields acquire vec, which are very non-hierarchical. They are actually quite compatible in all the elements. And that's what leads to these large corrections due to the kinetic term. All right. So once a symmetry is broken, generally there are corrections to the kinetic terms. They are present. And you just cannot turn them off because there's no symmetry to turn them off. There's a correction to the kinetic terms. They can be along different directions than the renormalization group corrections, even though formally they look very similar, right? But they could be along different directions. And the size of these corrections to the kinetic terms actually could dominate over the RG corrections. And this is due to the fact that there's no loop suppression, and you could have copious heavy states that contribute. They are subdominant for the quark flavor model because the flavor on that pattern are not hierarchical because of the small quark mixing. But they could be sizable for neutrino mass models due to the discrete family symmetry. And this generally can lead to non-trivial flavor structures or even non-zero CD phase.
One question.
Yeah.
Do these corrections to the kinetic terms, do they correspond to dimension 5 operators in the effective theory?
Dimension 6, I believe. 6. Right, so they go like 5 Degger. Basically, include two scalar, right? 5 Degger.
Okay.
And that's why you cannot turn them off.
Right.
Right. Any other questions? And that also shows you the dependence of. Right, so it's 5 Degger, 5, and this is a kinetic term, right? So if you have a 5 which is along the 1-1-1 direction, you can expect the corrections will be large and it may lead to non-trivial flavor mixing. Where for the in the case of the quarks, it's very hierarchical, and therefore such corrections are small for the quarks. All right, so here to show you one effect, like how big these corrections could be. And again, I'm taking this very vanilla version of the A4 models a la Verruccio and Alpha Rayleigh. Where theta 1,3, remember, is 0, right? So that's the example I showed you earlier. And what I plotted here is the range for the lightest neutrino mass, M1 mass, going from 0 all the way to 0.1 electron volt So this range from the very hierarchical mass pattern all the way to near degenerate mass pattern. The vertical axis here is corrections to theta 1,3 on top of the model prediction, which is 0. Yes, model predict leading order is 0. And this is a correction due to the correction to the kinetic term that leads to non-zero theta 1,3. So the bottom line is, what you can see here is that once we get to this near degenerate spectrum for the neutrino masses, the correction to theta 1,3 become really large. They can be as large as 8 degrees, which is compatible with the experimental result.
I have a question
sure.
in connection with it.
Yeah.
It's clear that these effects are coming from the running of the relations of the parameters.
No.
This is in addition to the running.
Yeah, or in addition to the running. Yeah, but then when you look for relations between the parameters
right.
due to the symmetry, these relations occur at the high energy scale. And then if you have a running, then really one cannot see how these relations could be checked by experiment. It's not a question of precision because you have to include the running.
Right, sure. So I think the right way to look at it is that even though the model can may claim that I only have 2 free parameters, but effectively you have more because of this uncertainty. Does that address it?
Yeah.
Right, so I think that the better way to look at it is, even though I say this model may have, say, 9 parameters or 2 parameters, right? But that doesn't really include this uncertainty that due to the corrections to the kinetic terms, which is out of our control, as you said.
Okay, thank you.
All right, so that uncertainty can range between 0 to 8 degrees. And then you can question how robust is this theory prediction, right? And of course, if there's a reason that allows us to control this corrections, that probably would be something interesting to look at. All right, so this is theta 1,3, and right, so this is a corresponding using the same set of parameters, and this is for the corrections to the solar mixing parameters. And once again, once you get to this near degenerate spectrum for the neutrino masses, you get quite sizable corrections. Even though this case, the correction to theta 1,2 is 1 order of magnitude smaller compared to the correction to theta 1,3. And one way to understand why the near degenerate spectrum give you larger corrections, one may look back to the renormalization group equations for the neutrino masses. And generally, if you want to look at the correction to, say, mixing angle theta ij, this goes like roughly the sum of the 2 masses divided by the difference of the 2 masses. So this is the beta function coefficients for the rounding parameter for the neutrino mixing angles. And this, with this relation, that allows you to see why, when the 2 masses are degenerate, that would drive the corrections to be large.
Yeah, in connection with that, probably there is not only the running of the variation with the mass and so on for each parameter, but probably the coupling of the different runnings.
Right, so that should all be included.
All of them.
All of them, yes, it's a system. I agree. It's just I want to do it, intuitively, just to show why it is so. This is like very schematic, but I agree. It's all coupled. Yes, very good.
And what kind of seesaw mechanism is that here? Type 1?
This is, in their case, this is type 1. Yes, this is with 3 neutrinos. Yes. With 3 neutrinos in the A4 models, and the flavon acquired particular pattern of web. One is 111, and the other is 100. Right, so that's simplest version. So that's what we did the analysis on. And then, of course, these 2 flavons will then couple and couple to the kinetic terms and leads to such corrections. And again, this is in addition to the RG running, right? So again, takeaway message is that there exists uncertainties due to the corrections to the kinetic terms that we have to keep in the back of our mind. And again, this is the corrections to the atmospheric mixing angle, which is rather sizable, 1 degree, for near degenerate spectrum, and it is of opposite sign compared to the other two corrections. All right, very good. Good. So now come to the aspect of CP violation, and I know Jose will talk a bit more on Friday, perhaps.
Yeah.
But here I'm just going to concentrate on one spatial properties of the discrete groups for CP violation. All right, so just to remind everybody, in order for CP violation, okay, if you have complex mass matrices, or let me say it in another way, to have CP violations, it requires the existence of complex mass matrices. And to see that, here I use the example of the up quark sector, but this, of course, can be generalized to the down quark and the lepton sectors. So what I show you here is the mass terms for the uptight quarks, right? I and J are the flavor indices. And big M here, this is a 3x3 mass matrix. This is its conjugate, Hermitian conjugate, so that they preserve the CPD invariance of your Lagrangian. Now, under CP transformation, the operators get mapped to its conjugate. But the mass matrix itself, being a C number, they stay the same. Right, so now if you compare the CP transformed Lagrangian with the original Lagrangian, what you observe is that in order for CP to be preserved, the mass matrix must be real. And vice versa. If you want CP violation, then the mass matrices must be complex. Right? So that's all at the phenomenological level. And now you can ask, at a more fundamental level, how does CP violation arise? Given that the mass terms are due to the Yukawa interactions, like in the quark sectors or Charles-Lepton sectors. So conventionally, there are two ways that CP violation can arise. One is called the explicit CP violation, which is due to the complex Yukawa coupling constant in the Yukawa interaction. So if you have explicit, if you have a complex Yukawa coupling constant, then that explicitly breaks CP because your Lagrangian doesn't have that CP symmetry. CP violation can also arise spontaneously due to the complex web of the scalar fields. So that's called spontaneous CP violation.
Yeah, but then you need more than one thing.
Sure. Right. Yes. Good.
You observe only relative phases. Yeah?
Yes, only relative phases is physical. Yes.
For relative, you need more than one.
Sure. Right, but this is just a gross classification of the two ways, and of course, to build models that require a lot more details that you need to consider. All right, but there's a new option in the presence of the discrete group. Namely, in certain discrete groups, the Cauchy-Golden coefficients are complex. And then this leads to discrete CP violation, but it is determined by the group theory. Right, so it's a bit, some people call it geometric CP violation. And this mechanism can work both in quark and lepton sectors. Namely, the observed CP violation in the quark sector and the hopefully observed CP violation in the lepton sectors can both come from the complex Cauchy-Golden coefficients. And the whole idea is that this Cauchy-Golden coefficients in the non-abelian discrete groups give rise to relative strength and phases in the entries of the Yukawa matrices. And this leads to the mixing angles and phases, and hopefully also the mass hierarchies. And if this can be achieved, then we will have a very, very predictive framework. So this is a cartoon picture of this idea, where I started out with some discrete group G, all right? And suppose the standard model Higgs doesn't transform under that discrete group. So it doesn't carry any family symmetry quantum number, where the two generations of left-handed fermions and right-handed fermions, they both transform as doublets. And suppose, because of the group theory of G, to form an invariance operator, you need to couple this 2 cross 2 to a triplet scalar, the so-called Flavin fields. These are, you can think of this as a Higgs field, a scalar field, which breaks the discrete family symmetry. All right. All right. So this is one operator which is invariant under the discrete symmetry G. And given that this is only one operator, there's only one single coupling constant. Right. But now I can write out these operators in terms of the elements in these two fermion doublets, right? And the coefficient Cij here, this is the Clebsch-Gordan coefficients that tells us how to combine all these 3 representations together to form a singlet. All right, so there's a Z3 symmetry in your scalar sector that tells you all the 3 elements in this triplet Flavin fields are equal. And this leads to a defective mass matrix of this form. And what's special about it is that all the entries, only the Clebsch-Gordan coefficients appears in the entries. And if these Clebsches are complex, then this could lead to CP violation, right? Out of the complex CG coefficients. So this is the basic idea of the mechanism. Right. So this is a nice scenario where CP violation can come from field theory. And this comes about, so I can go into more details and maybe Michael will discuss it later. But what happened here is that if I started out with a Lagrangian, I can apply the canonical CP transformation, like what you learned in Peskin and Schroeder, right? The field phi gets transformed to phi star, right? All right, good. And then we could transform under this group G family symmetry and apply that transformation on the Lagrangian. So what happened is that after the canonical transformation of CP, canonical CP transformation, this Lagrangian may no longer has the original symmetry, or original flavor symmetry. So in other words, there's a clash between the group transformation of your family symmetry and the CP transformation. And you may have heard of something called the generalized CP, which basically combine the canonical CP with a unitary transformation. And together, this could be an automorphism of the group G that you started out with. But, and by applying this automorphism, you may maintain the invariance of your Lagrangian with respect to the original Lagrangian. But the bottom line is that not all the groups possess such automorphism. And therefore, in such scenarios, CP is spontaneously broken in a generic setting. Right, so I know this is a bit technical, and I'll be happy to chat more about it later. But I thought I'd just put out this interesting possibility, which is what we are not so familiar with a continuous group. Right. So here, if you have a non-abelian discrete groups, the Clebsch-Gordan coefficients can actually be complex, and that leads to actually quite interesting possibility in terms of the predictions for CP violation. All right. So of course, once you generate a non-zero Dirac CP phase, that leads to Leptonic CP violation, and there is a large experimental programs trying to search for that phenomena. And that phenomena may be relevant for baryogenesis. So I think this is probably, I can skip the stereoneutrino part and come to my summary. Alright, so for the first part of this lecture, I hope give you some flavors or convince you that the fundamental origin of fermion mass hierarchy and flavor fixing is still unknown. And neutrino masses give us one of the very first solid evidences of physics beyond the standard model. Here I spent like most part of the lecture and try to convince you that symmetries can actually be very useful tools. They may provide an understanding of the patterns of fermion masses and mixing by combining grand unified theories and grand unified symmetries and discrete family symmetries. This could lead to some predicted powers, even though we have to keep in the back of our mind there's the uncertainties in certain setups due to the corrections to the kinetic terms, which may lessen the robustness of our theory predictions. Concerning the questions of Dirac versus Majorana, and this is specifically for the young people here, you should remain open-minded. Because I can tell you like many situations where we do a vote about whether neutrinos are Majorana or Dirac. Maybe we can do it now. How many of you think neutrinos are Majorana?
Everybody.
How many of you think neutrinos are Dirac? Right, so you can see that there's a difference between the demographic of the hand showing versus yes, the options. So I think this is actually really the experimental question. It's only experiment that can tell whether neutrinos are Majorana or Dirac, and we should let our theory prejudice to dictate our efforts. So naturally, like Dirac neutrinos can arise from various scenarios, either due to SUSY breaking or warp extra dimension of Reynolds-Sundram type can also provide a way that gives you naturally light Dirac neutrinos. All right. So I think I will probably stop here, and on Wednesday I'll continue with leptogenesis. Thank you for your attention.
We have time for questions.
Thank you very much for your brilliant pedagogical lecture. Fantastic. You see, the question of Dirac versus Majorana, which you said is probably one of the most important trending questions, not only in neutrino physics, but fundamental physics in general. You ask, why is neutrinos are Dirac? I think this is a very subtle question, because you have to put many things at the same time in order to get Dirac. The first thing is that you need right-handed neutrinos, okay? But once you have right-handed neutrinos, they are singlets, yes, they are. And then, okay, why you don't put, if it's a singlet, there is a gauge invariant term with the singlet, okay? And then this is a Majorana term. And when you have both, then automatically you violate the lepton number into units because of the second term of the right-handed. That means at the end, even with this logic, neutrinos, even in that case with the sterile neutrinos, they will be Majorana because of the violation of lepton number. That means the field with definite mass will be Majorana. The only thing to avoid this logic is that you have to put by hand that this term is forbidden. Right-handed, right-handed. Okay? Once you put the sterile neutrino. But this is against our dogma, that you have to put in the Lagrangian everything that is allowed.
But you could just add some C4 lepton number, then it's forbidden. I mean, you could just say there is a C4 lepton number symmetry, and it's forbidden.
Yeah, you have
then it's consistent with the dogma.
You have to put the symmetry.
Yes.
That the lepton number, is conserved. But why the lepton number is conserved?
No, you
This
cannot
term
just
is allowed.
conserve lepton number.
You
There
see?
are anomalies, but you can have a
You have to put by hand.
Right, so I think another way to look at it.
My question,
yes,
in fact,
sure,
my
sure,
question,
sure.
this is a comment, but my question, in fact,
Can I
is,
comment to your comment
my
first?
question is whether in these models
Yes.
that you see, in which really you can generate a Dirac mass term from supersymmetry breaking and so on. Is it possible to understand lepton number conservation?
From the symmetry.
That in supersymmetry, or in some models, that means instead of putting
Right.
lepton number conservation by hand,
Right, right. So you are asking, so there are different labels, right? So let me try to answer that
it's
in one
not
level.
a question only of what is the Yukawa coupling,
No, I understand, right? So let me try
but you
to.
have to put lepton number conservation.
Right, so here, so just give you one example, and this is not the only example. Here we have a Z and R. It is anomaly free, so that already constrains your model a lot. And this is a symmetry that get put in not just to forbid the lepton number, but it also does other things. It also, prevent the mu term from getting too big, right? That's bonus number one. It also forbids dangerous proton decay. The dimension 5 proton decay operators are also forbidden, and etc. So there are many other benefits or other problems that get addressed with the same symmetry you have. And the symmetry, or more precisely, the discrete charges of your fields are what is the word? Are restricted by the anomaly cancellations. So I hope that in one way answer your question. This is not just I put in one symmetry just to make neutrino Dirac, but I put in this symmetry to address many theoretical problems that we have. And one of them, one of the added bonus, I mean, neutrino being Majorana is not a problem, but in this type of framework, what I try to say is neutrinos can be naturally Dirac. So that's one label. And another label, if you want to ask, where does that symmetry come from? From a more UV theory, like from string, or why do the particles have a particular set of the R charges? Then I cannot address that, and that we probably have to refer to various string construction and see whether there's more fundamental way that this symmetry can arise, maybe from geometry. Sure. Yeah.
Yeah, I want to take up this question and take it even one step further. I mean, shouldn't the question actually be how much Dirac are the neutrinos? Because even in the standard model, I mean, we know that there is Barrow number violation by some unobservably small instantaneous process or something like that. I mean, isn't something analogous happening with delta L? And if so, doesn't that mean to some really unobservably small level, there will always be some violation of delta L, and therefore there will be induced
Once you have, it doesn't matter what is the level in which delta L is present,
exactly.
then will become Majorana.
I mean, it can be negligible for all practical purposes, but as a matter of, is it this or is it that? Isn't the answer it's always Majorana, but it could be completely dominated by Majorana?
Want to say something?
No, it's not, because, I mean, you see, if you're now referring to these standard model B plus L violating processes, you also observe that the violate, for instance, baryon number by 9 units. And the reason for that, or one way to think about this, is that there is an anomaly-free C9 baryon symmetry, which is unbroken to all orders. It's only really that there's the violation by 9 units. And you can impose an anomaly-free C4 lepton symmetry, which is just unbroken. This doesn't mean that lepton number is unbroken, because lepton number is violated by 4 units, but not by 2. So there will be never in any level at the perturbative or non-perturbative level any lepton number violating operator which violates lepton number by 2 units. This you can completely kill off. So it will never come from the anomaly. The anomaly still respects some discrete conservation laws corresponding to the non-anomalous discrete subgroups.
So this is really to all order. I mean, they don't appear. Those perturbatively and non-perturbatively. And we check that. We understand that. Yes.
No, in the standard model.
In the standard, in MSSM.
And in
Right.
MS.
Right.
Perhaps I would like to say something. Independent of any details, it's only a question of elementary quantum mechanics. Okay? You see, when you have a Dirac master, whatever is the origin, okay? Dirac master, I'm not saying that neutrinos are Dirac.
Right. Right.
I write the Dirac master,
Right.
that means left-handed, right-handed.
Sure.
Then you have the same for the conjugate. And they are degenerate, okay, because of CPT. It's like that. Then, no matter, this is quantum mechanics, when you have two states which are degenerate, no matter what is the amount of the perturbation breaking this, then automatically you have the mixing, complete mixing between those two states. The star mixing using atomic physics or whatever that means, okay? Then automatically you have complete mixing. That means the physical states of mass will be, you see, maximal mixing between neutrinos and antennas. And this is the Majorana independent. As long as you put, no matter what is the amount of delta L equal to 2 in your Lagrangian, then the physical states of mass will be Majoranas.
Right, but once you put that in, the whole picture
Because
changes.
neutrinos and antineutrinos are degenerate of CPT. Okay, you have to break CPT if you want, but this is another thing.
But here I don't break CPT, right? Here there's the delta L equals to conservation.
Yeah, that
To all
means
others.
this is elementary quantum mechanics, okay? And you see in the books of quantum physics in the elementary level, you see in the Stark effect, in the atomic physics, okay? You have L equals 0, L equals 1 stage, and they are degenerate in the Bohr atom, and in the hydrogen atom, then automatically you have maximal mixing when you put an electric field. It's exactly the same problem. Maximal mixing, even if the amount of the perturbation is very low. Because of degeneracy. The degeneracy you have this degeneracy. If you put a preferred direction, no matter what is the amount of it, then automatically you will not.
We can talk about that more. But here, again, I think this is going beyond just the minimum setup, right? Because here really have a non-anomalous delta L equals to 2 conservation.
We have time for more questions, comments? No, let's think we can get. And we have 30 minutes for a coffee break. The second session of this morning, and Alfredo Galindo Ugari, we will talk about the search for neutrino-less double-bit decay.
Thank you, Eric. So it's a real pleasure to be here. I talk a little bit about myself in a few minutes. But I'm going to be talking mostly on opportunities of neutrino physics in connection with my home institution, which is Oak Ridge National Laboratory. The way I split the material is today I'm going to be talking about search for neutrino-less double beta decay, and tomorrow I'm going to be talking about coherent elastic neutrino scattering, in particular the project Coherent, and also on the search for stereo neutrinos, which is another project that we have that is called Prospect. So here is a picture of the Majorana demonstrator, just showing it's open, so just showing the setup. These experiments are done at the research facility at the mine in South Dakota. This is depths of 1 mile, and I call it the Cosmic Silence Lab. So this is just simply to illustrate that some of these experiments require extreme conditions in order to be done, and even that you are 1 mile and things are quiet in terms of cosmic rays. In addition to that, you have to deal with an incredible level of purity in the materials that surround your detector. So I'm also going to talk a little bit about analytical techniques, some of them that we are pioneering in terms of trying to detect the lowest levels, for example, of uranium and thorium in the copper materials that surround the detector. A little bit about me. I'm probably a local product. I am probably did my bachelor's degree many decades ago at the National University, and then after that I did my PhD at the University of Toronto. Then I did a postdoc, and then I was hired by Atomic Energy of Canada, the Chalk River laboratories. And then about 21 years ago, I went to operate National Laboratory. And I'm also a professor at the University of Tennessee, partly because I'm quite interested in forming the next generations of students. Both Chalk River and Oak Ridge, they have a lot of tradition in nuclear physics and also in neutrino physics. In Chalk River, for example, Bruno Pontecorvo spent several years working in there, and Oak Ridge as well has several things I will be talking about, and in particular I'm going to make emphasis on some of the infrastructure that we have at Oak Ridge in order to do some of this neutrino physics. So Oak Ridge is the largest non-defense national laboratory. We have on the order. It's a multidisciplinary laboratory that has relatively new in terms of neutrino physics. In fact, some of the projects I'm going to be mentioning here for the very first time, we're getting funding from high energy physics. Traditionally, we have got our funding from different areas, and in particular, one of the reasons I was at Oak Ridge was that we have the prime facility for a radioactive ion beams physics, low energy nuclear structures. My background is actually in nuclear physics. But as part of the infrastructure of this laboratory, there is a point-like, there are two fantastic sources of neutrinos. The reactor, which is a research reactor with 85 megawatts, which is twice the size of the Grenoble reactor, and it has a core of 20 centimeters, so it's really a point-like source of neutrinos. And secondly, it is the most powerful neutron source, which is the spallation neutron source, that we can use the pions at rest, and this is a pulse source, if you wish, of neutrinos. So tomorrow I'll talk a little bit about that and some of the initial results that we are getting from it. Let me make a historic remark. We have several international people here that might not know some of the history of the physics in this place. And just next door is the room for Manuel Sandoval Vallarta, which was a pioneer physicist in Mexico. He actually was a mentor of Feynman. And there were very important experiments were done in the theory of cosmic rays, in particular Sandoval Vallarta together with Abad Lemaitre from Belgium. They did a theory about the nature of cosmic rays, and some of the experiments that they were done were very, very important. The point I'm trying to make here is that a lot of these guys that are here on the wall many of them, they were influenced, and essentially they cascade down from the influence of somebody like Sandoval Vallarta. And the importance of some of these studies in cosmic rays, particularly on the 40s, on the 50s, was so big that there was, a few people know, that there was an American Physical Society meeting that was organized in Mexico City in 1950. And this was done at the Palacio de Bellas Artes. And it was inaugurated by the president of Mexico, by Miguel Alemán, which is a little bit unheard to hear that a physics meeting nowadays being inaugurated by the president of the country. So this is just a little bit of historical vignette. In fact, I'm particularly interested on some of the history here, and this is myself at the roof of a very old hotel that is in the Zona Rosa in Londres. It's called the Hotel Viennet, and somewhat I convinced them to allow me to go to the roof. They thought it was a little crazy. Of course, there's nothing on the roof really, other than very important experiments were done on what is called the east-west asymmetry of cosmic rays. In fact, there were experiments done by, at that time, Luis Alvarez. This is Compton and Luis Alvarez, and they sent him to work together with Sandoval Vallarta. And there was another fellow by the name of Harold Johnson from the Bartol Institute, and they did key experiments on the roof of this hotel to measure a 7% asymmetry east-west that essentially gave the clue that the main component of cosmic rays were protons. Millikan, which was a very influential fellow, he was pointing, or he was trying to push his way to convince everybody that the electrons were the main component of cosmic rays. Literally, these things were done on a wheelbarrow with Geiger counters. And if you want to learn a little bit more, you can look at several papers that I guess Alfonso Mondragon wrote about the history of this event. Anyway, this generated a lot of interest, particularly Marcus Moschinsky, Tomas Brody, and many people were formed in this country in nuclear physics. Then there were efforts in experimental physics, and then people branched out into geophysics and so on. So I mentioned that because a few people have this information. Another point is not only the influence was within the physics itself, but it also had impact in other sciences. This is an architect, Felix Candela, and this is the so-called La Muela. It's a tooth. This exists is basically going more towards the main campus, and essentially was a cosmic ray pavilion that operated for a long, long time. The key here was the design, this particular form of hyperbolic paraboloid that allowed very, very thin thickness on the structure, which was very important for the cosmic ray detection. So for many years, there were counters in here that they were taking very important data. This, by the way, the National University in 2007, about 10 years ago, it was declared a World Heritage Site. Okay, back to my talk. I'm going to be talking, and this I think connects quite nicely with the previous talk. I'm going to talk a little bit about Majorana neutrinos and the mass hierarchy, the neutrino-less double beta decay, why do we bother to do it, show that this is an international effort, show specifically about the Germanium 76 effort in the form of the Majorana demonstrator and legend, which is a path to the ton scale experiment, some of the R&D accomplishments, and some techniques that we have been developed on ultra-low background techniques. So these are some of the current interests from our group. We're interested on the Majorana demonstrator, which is a 40 kilogram array that has been running at South Dakota, and this is meant to demonstrate that one can go to the 1 ton scale in order to search for this process of neutrino and double beta decay. Tomorrow I'll talk about Prospect, which is a precision reactor neutrino oscillation experiment that is being done at our reactor. Coherent at the I'll talk about the first observation of coherent that was done with one of the detectors at the spallation neutron source. And today I would basically concentrate on the top topic of germanium neutrino double beta decay, and I will talk a little bit about some of the ultra-sensitive analytical techniques that involve single atom counting using techniques such as accelerator mass spectrometry, laser-based techniques. We're using some form of optical pumping, if you wish, resonant ionization using lasers, particularly in actinides, and some nuclear activation analysis capabilities that we have at Oak Ridge. So we have learned a lot of neutrinos over the past 2 decades, but as mentioned previously, and I'm not going to go through many of these things, that essentially there are still many questions that need to be answered, such as whether the lepton number is a conserved quantity, whether the neutrino is its own antiparticle, and some questions about the mass hierarchy, the origin of the neutrino mass, the absolute scale, and the right-handed sterile neutrinos that have been mentioned before. So starting with the beta decay, of course, in the case of several types of radioactivity like alpha, beta, gamma radioactivity, typically with alphas and gammas one deals with a discrete spectrum where basically one has emission between 2 quantum levels and one has essentially one tends to have one peak. In the case of in the 30s, when the beta decay was being studied, instead of that, a continuum was being observed, and if it was a two-body decay, one would expect essentially a similar situation as in the case of the alpha and beta decay. So at that time, it was an issue of whether energy and the loss of conservation of energy were being violated and so on. And you probably know the story that Pauli comes with this proposal about the neutrino. He calls it neutron. The neutron had not been discovered until 2 years later. And eventually Fermi comes and develops his theory of beta decay. So this is represented here by a single beta decay, sort of a three-body process where you have an electron, you have the antineutrino from the electron, and the question is whether one can have two double beta decay. So this is a second-order process, and it can only happen when the single beta decay is energetically forbidden, and in principle this allows double beta decay where you have the production of two antineutrinos, two electrons has been observed. And what we are more interested is on this process where essentially the final state consists of two electrons. So in the case of beta decay, for example, the tritium decay, essentially this is what's happening. A neutron is being converted into a proton, an electron, and an antineutrino. And in the case of the double beta decay, the two neutrino double beta decay, you have this as the byproduct. And the observed half-lives, this is a very rare process already, but in those cases that are energetically favored, it has been observed in about 11 cases, and the half-lives are extremely long. They are of the order of 10 to the 19 to 10 to the 21 years. In the case of neutrinos less double beta decay, essentially you have this process at the end final state, and this has not yet been observed. So if observed, as mentioned previously, this will demonstrate that lepton number is not concerned. Indeed, this is a very, very important question that has been focused the attention of two communities. Both the nuclear physics community and the high energy physics community are pushing for experiments along these lines. And it would show that neutrinos are Majorana particles, and of course it would have also some implications on the masses and the absolute neutrino mass through a model-dependent process. And essentially this is a process that has no neutrinos either in the initial or the final state. So how can we tell from zero neutrino double beta decay from two neutrino double beta decay? So essentially in the phase space, what we have is a continuum in a similar fashion as in the single beta decay. One would have this continuum. This is, in this axis is energy divided by the Q value of the reaction. And in the case of the neutrinoless double beta decay, the signature would be that we are detecting in the same, say in the same detector. The detector is the source of the neutrinos, and also is the detection system. What we would see is a small peak at the Q value, where that would correspond, or that would be the positive signature that indeed we are observing double beta decay neutrinos. So essentially the process is relatively simple, except that this peak relative to this peak is several orders of magnitude smaller. So the decay rate is regulated by this expression, a phase space expression, terms that correspond to a nuclear physics quantity. These are the so-called matrix elements. So it's a many-body quantum system, and there is a lot of discrepancy between the different methods in terms of calculating some of these matrix elements. So in terms of theory and theoretical, nuclear physicists are trying to refine some of the theories, but up until now there is a very, very large discrepancy, and this is one of the main sources of uncertainty, because of course many of the half-life predictions are going to vary tremendously depending on these matrix elements. And then there is an effective mass of the neutrinos, as it was explained before, which is this weighted sum of the several neutrinos. So this is what is being plotted in this axis, and essentially these bands correspond to what is called the inverted hierarchy, and this corresponds to the normal hierarchy. And there are already current neutrino double beta decay experiments, and they are getting closer and closer, excluding some of these particular regions. But in order to reach on the inverted, we still have to go even further, and to the half-lives of the order of 10 to the 28 if we want to fully cover the inverted region. And what I'm going to try to show to you is some of the detection systems that people have been using worldwide, some of the pros and some of the cons of these efforts, and try to give you a little bit of an idea of the scale of the effort and why this is a monumental problem, even that is certainly considered one of the top physics questions nowadays. So the covering the inverted region, the next generation sensitivity should try to cover this region. That is, as mentioned before, these are the typical numbers for this element. We are talking about 15 milli electron volts, that requires sensitivity of half-lives of 10 to the 28 years. And this corresponds to 1 decade per year per ton of material. So this is really a monumental problem that would require very, very large detectors in order to try to tackle this. And of course, getting into the normal hierarchy would require orders of magnitude of that. And at some point, the question is whether the scientific community wants to invest on a project of that particular magnitude. Depending on, of course, one can be running for 10-ton years of exposure. One is trying to push the background rates as low as possible. And depending on the different background rates, again, the different predictions in terms of the exposure per years. So this can vary widely between these, and some of these things will take a generation to be able to reach these values. So sensitivity requirements say 10-ton years of exposure. Essentially, the source is working as a detector. The material requires to be enriched. Of all these 11 candidates, many of them, they have a certain natural abundance, and in some cases the natural abundance can be extremely low. So one requires enrichment processes that are extremely that cost a lot. So for example, the germanium detectors that we have, the material costs more than making them of gold. So the process of the isotopic enrichment is problematic. The background rates in the peak region, one chooses a region where one tries to optimize, and in that particular case, these rates are very, very small. One requires the best possible energy resolution of the detectors. One requires only ultra-clean materials, and people have been playing with other tricks in order to subtract to get the backgrounds low. Oh, here, wait a second. Okay. Requires some. This must be the height. I'm getting dizzy. Some require some active shielding. So people have been using things like argon, and I'll talk a little bit about that. And one way of thinking, and this is an analogy with nuclear structure, some of you might or not know. In the case of nuclear structure, there have been we're building up already on some technologies that people have been using, for example, to study gamma ray spectroscopy. Gamma sphere is a detector that was built by the international community, by the national community in the US, mostly pushed by Berkeley, of 110 germanium detectors. And essentially what we would need in order for the next generation of neutrinos, the double beta decay, would be to build 7 of these things out of instead of being natural germanium, it will have to be enriched germanium-76. We could only use ultra-clean materials for the cryostats, for the readout, for the cables. Every single piece that is surrounding the area, we have to make assays in order to determine at the very, very low levels the amount of potential material that can give us a background on the region. We have to bury it in a shield 2 kilometers underground, and we have to run for 10 years, and then we have to look for a peak with less than 10 counts at the Q value, which in the case of germanium-76 is 2039 keV. So this here is an illustration of how hard it is. You have a logarithmic plot on the here in the vertical scale, and this would be what would be a background on 1 kilogram surface-based germanium detector, shielded by about 12 inches of clean lead, and this is what you would observe on the surface. So you have to go several orders of magnitude in order to see the 2 neutrino double beta decay, and then your signal will be here, and I have already exaggerated by a factor of 10. So it really is an unprecedented background levels that we require in order to do this, and that is a considerable effort that we have to deal with.
This, let's say, the expected scene at this for 2 neutrino beta beta. No?
Correct. So we
this, in that case, energy resolution is not for 2 neutrinos. For zero neutrinos, probably your result depends on what is the energy resolution.
Correct. And this is an issue at the core of which type of technology should we be using in order to do this. You require tons of material, and of course there's a limit of the type of technologies. Germanium has been a mature technology that has been used by essentially all the nuclear spectroscopy is done on germanium detectors. Is the main workhorse, and there are next generation of tracking devices that have been developed in order for nuclear physics, and it's an exquisite response, and it can be produced extremely clean. So at issue, of course, you might have xenon on a very large tank that is somewhat cheaper, and it's monolithic. It's essentially you have a single volume of detection, and in that case you might be buried in the expected. You have to observe, of course, the 2 neutrinos double beta decay, and then the question is how well you can define this region. So there is the distinction of discovery potential versus establishing a limit. So that is basically what we are fighting, if you wish, because at some point we're going to go through a down select process with the funding agencies about which should be the technology we should be using. Yeah.
Why do you have those wiggles in the
here
in the black? Why?
Here.
Like the other part. Why is it
This portion is
Yeah.
just the statistics.
Okay.
It's just fluctuations on the statistics. So it's all about backgrounds. So essentially you want to go deep, and for the next generation it's not clear that the existing mines are enough. So there are several places. Sudbury is one of them. Sudbury is a very, very favorable place. Sudbury can go to about 7,000 feet. There's a mine in China, and there is even a project in South America that is called Andes, that they are talking about a tunnel to go through the Andes. It would be between Chile and Argentina, and the possibility is to put some kind of another Gran Sasso place in there. So the question that the community is trying to push right now is whether the depth is going to be good enough for the levels that are required. So the muon creates high and low energy neutrons in the rock. The neutrons, they excite the materials that are surrounding, like lead, copper. The neutron is then thermalized and captured. You can have alphas coming out from radon daughters that can give you signals above 5 MeV, and that can cover some of the region of interest. And we have developed some methods by essentially these detectors are fully digitized, and by looking at the traces and the slopes of the traces, we have been able to protect about events that are happening, for example, on the surfaces. This was a major contribution that we did in the case of the Majorana to reach the limits that were required. There is natural radioactivity in the materials. For example, the chain of thorium, the chain of uranium, in particular these transitions, bismuth 214 thallium-208, they are above 2 MeV and they can give you a signal on the region of interest. The problem is how to make pure materials. And we talk about purities, but reaching the levels that are required are very, very difficult. And even if you reach those levels, the problem is that you might not have the analytical techniques to be able to determine that you have that kind of levels. So that's why our interest in terms of developing new techniques to prove that indeed we have reached the level. You don't want to build the whole thing, then measure the background and find that your materials were not clean enough. So what we want to do is sample every part of material that is surrounding, minimize the amount of material that is surrounding your detectors, and then having assays that can be involved single atom counting in order to get the backgrounds that you require. There are problems associated with cosmogenic activation. So for example, high energy neutrons and muons, they break up copper and lead, and they can make radioactive isotopes, germanium-68, cobalt-60. So they decay and produce betas and gammas in the region of interest. So how we are dealing with it? Well, muon-induced, we go deep, we go underground, we have muon betas, we have neutron shields, alphas, again, ultra cleanliness. Even at the mine, we're working in globe boxes. Cosmogenic activation, we minimize the above ground time. For example, this material is produced in Russia. It never flies. The material is being sent on a ship with a lot of shielding. Then we store the material on a relatively shallow cave. We extract the material, send it to the manufacturer. So around Oak Ridge, there are several of the main manufacturers of germanium detectors, such as Ortec and Canberra, and a company called EH. What we do is we minimize the time of processing. Once they build the germanium detector, we essentially have someone driving all the way to South Dakota for nearly 24 hours in order, and somebody in South Dakota is going to be receiving the material. We'll have I wouldn't call it an elevator, it's a cage where the miners go down. It's a very smallish cage, and then the material will be going down and stored on the ground, essentially to avoid the transmutations that are happening at the minimal amount. It's not a tremendous amount, but this is enough to have to be an issue for some of our detectors. In terms of the natural radioactivity, we need high radio purity, and the rooms that we have downstairs, they are literally some of the cleanest rooms anywhere on Earth. So everybody is working on this money rabbit type of clothing, and there is an incredible extreme protocols in terms of the cleanliness, in particularly for this germanium-76 effort. So candidates for neutrino-less double beta decay, there are these 11 candidate isotopes. They range from calcium-48, which unfortunately has a very large Q value, but it has a very low abundance, to about to neodymium-150. And they have been, as I mentioned before, the decay half-life being already measured for the case of the two neutrinos, with this exception. And the current best limits from half-lives are coming from three isotopes: germanium-76, tellurium-130, and xenon-156. They all require enrichment, with the possible exception of tellurium-130 that has a natural abundance of about 34%. So detection techniques, I'm going to give you a broad idea about how this is being done. So you have detectors that rely on ionization. So the case of Gerda in Europe, which is basically our competitors for Majorana, they use hyperpure germanium crystals, or in the case of tracking and our calorimeter super NIMO. These detectors essentially they depend on the production of pairs of electron holes on a germanium detector that are being collected, and then that is transformed, that is amplified, that is transformed into a useful signal. I'll show a little bit of the tricks that we are using nowadays with some of the crystals. Or we can have kind of a more classic type of detection, which would be whenever you have the interaction on the material, you can have light. So essentially these detectors work on materials such as liquid scintillators produced at the massive scale, like Camel Scent, like Snow Plus, and essentially they rely on the amount of light that is being produced and having a huge amount of sensors like photomultiplier tubes that are going to register the signals. There is something that is a little bit more recent, which is the use of bolometers. So cryogenic techniques, some people in the 80s, they found out that in principle one could have a thermal pulse. So essentially what one is having on the material is producing phonons. These are bolometers that are working at extremely low temperatures, which they have their challenge in order to be able to have large amounts at the scale of tons based on this type of technology. So the cryogenics can be complex and it can be a difficult experiment to be done. And then there are connections between these things, such as combination of ionization and scintillation, such as TPCs like EXO, NEXT, and so on. And same thing here, there is link on scintillators and bolometers, where people are trying to get also some additional signal coming out from the bolometers in order to get rid of some specific backgrounds associated with some of these techniques. So in the case of scintillation, Camel Scent and Snow, they are in the xenon and tellurium isotopes. Many of these detectors, they already existed. They have been, some of them they have served a purpose before. They are being sort of retrofitted specifically for the neutrinoless double beta decay searches. They have a big advantage that they can be scalable. So in principle, one can make something that is bigger in size, limited by your resources. And you can use fiducial cuts to reduce your background. That means you can limit the amount, the central portion of the detector, and use the rest of the detector as shielding. However, in the negative side, they have the poorest resolution. So typically, you're dealing with about 400 kb full width half max. There can be issues with backgrounds, and they as I was mentioning before, there is this debate of whether they are useful in the sense of establishing a limit, but how useful they are for discovery, it remains to be seen. Time projection chambers, where we have scintillation plus ionization, and there's a series of EXO, NEXO, NEXT. They allow to do multi-site event rejection. That means if you have signals that are not happening at the same time on the same portion on space, you are able to, if there are tricks in order to be able to reject those. You can also use fiducial cuts, but again, the resolution is not that great. So this is just simply to illustrate where one of the useful signal falls. So you really have to characterize your backgrounds extremely well. There is one aspect associated with some of these time projection chambers, which is as you do the double beta decay, you are making a transmutation and you are going to something that is to a new nucleus. If you are able, for example, in case of xenon, if you are able to detect the daughter nucleus, such as would be the case of barium, there's something that's called barium tagging. If you're able to detect that, yes, your backgrounds would be, the coincidence technique would be such that you would lower tremendously your background. And there's a full army of people who are trying to do many of these techniques. In particularly, there's a group from David Nigren, the fellow that invented the TPCs at the University of Texas at Arlington, that they are working on trying to detect the barium. If they are able to do that, they certainly would have, that would be transformational, and they would have a lot of advantage if they are able to do something like that. Then there is bolometers like Quarry that is operating at Gran Sasso. That Quarry consists of single crystals of tellurium oxide. They are operating at very low temperatures, 10 millikelvins. They have this particular type of readout, and they require the world's largest dilution fridge in order to operate this device. They have very good resolution, about 5 keV full width at half maximum, but there are some issues associated with surface alpha backgrounds that they cannot deal with, plus the complexities of cryogenic operation. So there is quite a bit of R&D to develop bolometers that scintillate in order to be able to do this alpha rejection. Finally, the ionization, that would be the case of Gerda and Majorana. Again, Gerda at South Dakota, and Majorana at, Gerda at Gran Sasso and Majorana at South Dakota. These are semiconductor detectors, a P-type point contact germanium detectors made of 87% enriched germanium-76, operating at 80 Kelvin, liquid nitrogen, which is not too bad, and they have the best energy resolution. You can achieve 3 keV full width, half maximum, and you are able, based on the pulses, to do multi-site background rejection. So germanium-76 advantages over other candidate isotopes is the very high purity that is intrinsic to these semiconductors. Same thing as silicon, germanium can be produced extremely clean, an excellent energy resolution of the order 0.14% of the Q value of the value of interest, powerful background rejection using pulse shape discrimination techniques, digitizing the signals and getting out various cuts that allows us to reduce the background considerably. This is a well-understood technology, so there are commercial germanium diodes that the companies have been developing over the years. There is the nuclear physics community, very large germanium arrays such as Gretina, Greta, Gamma Sphere, and more recently there is the development of what is called point contact detectors, and I'll talk a little bit about that. So essentially the germanium is the source and the detector. So what you have to do is you're not detecting things from the outside, you're detecting things from the inside, but now you have to make a very, very large amount of material at the level of 1 ton in order to be able to do this. So there is a demonstrated ability to enrich from natural 7.8% to 87%. Currently, the Russians have the technology to do some of these things using gas centrifuge. Oak Ridge has traditionally what the fame of Oak Ridge was on the isotope enrichment, and we believe that we can convince the Department of Energy that we might be able to tackle some of the enrichment at Oak Ridge with new capabilities that are being built. So the Majorana demonstrator has been running for some time. This is a big cryostat that two of the cryostats, each cryostat has about 20 kilograms of germanium detectors, and they look essentially like a hockey puck. The materials, the copper that is surrounding the germanium has been made underground. So essentially what we do is a process of electroforming. So we have very large tanks 1 mile underground, and essentially what you have is an electrode, and you collect the copper, and the copper starts growing on the electrode at the level of is lower than how a nail grows. So it really takes literally months in order to produce that material. The material is taken out, and then essentially what we have is a machine shop downstairs, down the mine, where all the materials have been produced, and the machine shop itself is a clean room. So this is 1 mile at Surf in Leeds, South Dakota. There's a new development that is called the point contact germanium detector. Essentially what a semiconductor is a capacitor, and what you're doing is you're forming charges inside electron holes, and you're collecting it into electrodes, and that's basically what it is. Depending on the size of your electrodes, the amount of capacitance that you have on the material, and what you want to do is reduce the capacitance in order to have the lowest thresholds possible. These types of technologies, I should point out that they are also applicable to many other important searches nowadays in physics, such as dark matter detectors, coherent neutrino scattering. Essentially what you're trying to do is to lower your backgrounds and to reduce your thresholds of detection. So any of these advances that are being done can also be applied to some of these other areas. So essentially what we have done is, in fact, this was an invention done at the laboratory that now has been, the commercial vendors are doing it, and it's essentially to track the path where the electron and holes are being produced, and then because of the newer technologies on digitizing the signals, essentially what we're doing is with high frequency, we're sampling all the pulses, and we're having as much information as we can in the process of the collection of the signals. And this can give us information about where in the crystal the interaction happened. And this is important for distinguishing, for example, this is a pulse from a preamplifier. Is essentially a single step function. In this particular case, you see some additional thing in here. If you look at the response function of your detector and you do the convolution, in this case, it corresponds to a single peak. In this case, it corresponds to several peaks. So this is indication that it's a multi-site event. You don't want that. You want a single peak, and then you want to reject all of this. So this is just to illustrate how the detector strings are being assembled. So even within the clean room, you have a glow box that has nitrogen flowing on it. You tend to have double globes inside, and there's a whole bunch of procedures that will go into the detail of how to handle the materials. You try to minimize as much material as you can around the detectors. In order to do that, these are the cryostats. So essentially you have a condenser, you are cooling up through a thermosiphon, you have a cold plate, and then you have the detector strings, and then you push this into the shielding in this way, and then you surround this thing by ultra pure copper material, and then you relax some of the condition of in terms of the purity. You have a radon enclosure, you have shields and panels. Again, I'm talking 1 mile underground, and the process is really very, very complicated to assemble this thing. This is how the material is done, the ultra pure copper. So these are the electrolytic baths. This is one of the big electrodes coming out. It has about 1 inch of material, of this ultra pure material, and then it goes to the machine shop there, and then you make the pieces out of it. The problem now is, how do we assess the purity of these materials, and that is basically a big issue. So the thorium and the uranium are essentially the decay chain. They are the main culprits of the potential backgrounds inside. And here leads me to a switch of topics, which is the possible use of techniques that depend on single atom counting. So accelerator mass spectrometry is one area that I have been involved since my days in Toronto. The technique, essentially what it does is use an accelerator as the detector itself, as the analytical detector. Instead of using the accelerator to produce a beam and then bombard something and have a nuclear reaction, we put on the source of the accelerator the material that we want to analyze. And this can be essentially milligrams of material. So for example, if somebody in Camland wants to fill with tons and tons of liquid scintillator, instead of doing that and having 10,000 photomultiplier tubes and then finding out that the amount of carbon-14 on the material exceeds what you require, what you do is you take samples of all the components of the liquid, of the scintillator itself, and then you try to analyze whether they have the corresponding carbon-14. So of course, these are coming out from petrochemical processes, and what you want is to have old material, things that are being just recently extracted from the interior, and therefore they have been shielded for centuries, and then use that material as your raw material in order to form the scintillator. So essentially what this technique has made a tremendous impact in many, many fields, and essentially what you are doing is using nuclear physics techniques where you put in your source, you put this tiny amount of material, you sputter the material, and then essentially you inject atom by atom through an accelerator, and then essentially your accelerator as part of has a series of associated beam lines and electromagnetic fields. So you have electrostatic fields, you have magnets, and then you increase the energy. At some point you do a charge exchange process on the terminal. That is, you destroy the molecules. Essentially what the accelerator is doing is anything that has the same mass, you want to destroy it by the process of acceleration, and then you accelerate it to the point that you can use nuclear physics techniques. So essentially you can determine its time of flight and its mass. You can determine the charge by looking at the interaction of that charged particle in a gas detector that is going to be unique to the sea of that material. And by doing that, people have been able to establish this as a very well-established technique. Mostly it's used as a carbon-14 machine. In fact, this institute has one machine. I think it's here, next door. Okay, and what we did for some time ourselves at Oak Ridge, we used to have the largest tandem in the world. It was a 25 million volt tandem machine. You see the scale here with this person. These people have been trying to make miniature tandem accelerators. This is a ETH in Zurich, and this is 100 times smaller than this machine. And it works very well for doing carbon-14. So this is literally a tabletop. There are about 110 accelerated mass spectrometry facilities all over the place, and Oak used to have the largest tandem until very recently that we have been shut down as a radioactive ion beam facility to be placed to the next generation of radioactive ion beam facilities at Michigan State. So what we did in that case, just as an example of the sensitivity of this technique, was chlorine-36 is a radioactive ion. Chlorine-35 and 37, they are stable. And what we did is we took samples from different places around the world, half a liter of water, for example, at 4 kilometers deep in the ocean, and that is enough for us to do single atom counting at the levels of 1 part in 10 to the 16. So essentially, this is by far the most sensitive analytical technique. And this is the type of techniques that we're going to need if we're going to try to go for searches of neutrino less double beta decay, searches for dark matter, or in general, ultra-low background techniques. So essentially what we did here was to prove that there is variation of chlorine-36 on the seawater, and we push the limit of the accelerated mass spectrometry by an order of magnitude. What we are trying to do now is to apply this to actinides. So essentially we want to detect thorium and uranium in ultra-pure copper, and indeed we use some of the material that was produced on the mine. We do have, we developed a protocol, we developed a signal of how to detect thorium and uranium using one of these tandems. In this particular case, we use one at the Australian National University. We still need to develop a good standard to relate to this. But more interesting is a new development where one of my students, actually she's from UNAM, this is a PhD project and essentially what we're doing is, instead of using the conventional cesium sputtering sources that they have very small efficiencies of the order of 0.1 to 0.01%, if we want to push the limits, of course, a single atom counting technique relies precisely on going through tons of material in order to be able to see a positive signal. So we need efficiency on the source in order to do that. So what we have done, the technique essentially is 3 powerful lasers, and what we do is some form of optical pumping. So we go from the ground state, we dial a certain frequency that allows us, we need to explore the level schemes, the atomic level schemes, and essentially what we do is we go through one excited state, we have a second laser that takes this one to a second excited state, and then a third laser drives this into the continuum. So at the end, we basically have an atom that is positively ionized, and then now I can use electromagnetic fields in order to send it to the place of where I'm going to be doing the detection. The point is that now I have 51% efficiency. 1 out of every 2 atoms of plutonium, I can transport them, and I know that they have been ionized, plus the process is very selective. These 3 numbers, these 3 frequencies are a specific characteristic of that particular plutonium. So we are very, very enthusiastic about it. We did a test on essentially, this portion is a low energy mass spectrometer where the front end is this laser system. So we're collecting it in one place, and we had a small amount of plutonium that we have been diluting and diluting and diluting to the point that we have reached a sensitivity for plutonium that is on the 10 to the minus 18 grams. So this is without going through accelerators. It's kind of an accelerator mass spectrometry without accelerators. If needed, we might need to inject this into the tandem accelerator and go even further. But this is really something very interesting, just as an potential application. People have speculated about the possibilities of the explosion of a nearby supernova. And iron-60 and plutonium-244, these are long-lived but not as long-lived, so this is a chronometer. And if you search for traces of these elements, for example, in deep sea sediments, and you look for plutonium-244, this was an article that was produced was published in Nature about the plutonium-244. So this has connection with the possible formation of the heaviest elements, which, as you know more recently, because of this multi-messenger astronomy and LIGO, now they believe is that some of the heavy elements are being produced on neutron star mergers, but it would be also very useful to know and get some additional information coming up from the possible traces of some of these nearby explosions. So this is just an aside of how developing a technique for one field can have an impact in another field. So for the Majorana, essentially, I'll go quickly through this. This is the region of interest with all the potential cuts. We're basically reaching the levels that we needed. This is in the case of Majorana. Again, the same germanium detectors that we're using. In this particular case, these are the detectors where we have controlled the exposure at the surface of the rich material, and you see the red one is the one that has been kept underground versus one that was kept on surface. And this is essentially giving you a lot of background that this is tritium dominated at the low energy level. So tomorrow, when we talk about coherent and when we talk about essentially a dark matter detector relies on the recoiling nucleus at a very, very low energy level. So it's, the high energy physicists are looking now at the response, the lowest threshold and the lowest and the highest purity that you can achieve on very, very low levels. And in fact, the germanium detectors have been used also for doing some searches for dark matter. So again, next step, the nuclear physics community in the US gets together, people from the UAE, National Science Foundation, and in Europe there's a similar plan in NUPE, and in the high energy physics there's a similar type of activity, the so-called P5 report. So in both cases, the recommendation is the timely development and deployment of a US-led ton-scale neutrinos double beta decay experiment. So Oak Ridge is planning to take the lead on the project. So we are pushing. This is Majorana. This is Gerda. Gerda has taken. I won't go through all the details, but they took a different approach of how to suppress the background by essentially immersing the germanium detectors in liquid argon, similar temperature as nitrogen, except that they can get light through some fibers and they can suppress some of the background. And indeed, this worked out extremely well for them. And what we are doing now is joining forces and we're going to be using the ultra pure techniques where was the emphasis done on Majorana with some of these active argon chill. Argon has some isotopes that they are radioactive. Has some, we need to be careful as well as to the argon. We're developing some shrouds made out of a plastic materials called PEN that we think that is going to allow us to reduce some of the backgrounds. This is, incidentally, these are the Gerda results on the region where we expect the signal. So we're really getting very close to almost the zero background with this type of technology. So the new collaboration is called Legend. This is working towards a 1 ton germanium detector experiment. This includes, as I mentioned, Europeans, the US, and new collaborators from China, Sweden, British, and so on. So this is a very large collaboration that we're planning to push the limits in terms of this device. This is going to be done in 2 steps, but it's called Legend 200. Legend 200 will use infrastructure at Gran Sasso for Gerda. Essentially, the same cryostat is going to be the size of the top part, the entrance is being increased, and it can accommodate of the order of 200 kilograms. The Europeans have come already with the funding. National Science Foundation came recently with 7.5 million for germanium detectors, and we are going to be pushing, and this in principle is predicted might start as early as 2021. So this funding is kind of an intermediate stage. We really would like to go for the 1 ton, but the funding has come out, and we think that that will keep the momentum in terms of pushing for the next step. We're talking about these point contact detectors, and to reach this type of background goals of counts per ton per year on the region of interest. So the subsequent stages is a new cryostat, 1,000 kilograms of germanium. They also using the technology of liquid argon, and here we are competing with the other experiments on the xenon experiments, and there's going to be what is called a down select process in order to determine which project is going to be funded. Again, background goal is even lower. The location is to be decided. It's possible that current places that we have, both Gran Sasso and the mine in South Dakota, might not be deep enough, and this is still something that requires more simulations in order to see where the backgrounds are. Again, this is just simply pointing out a study that was done on what we call discovery potential, rather than just establishing the limits, and these are the 2 distinctions between Legend 200 and Legend 1000. Again, we're very enthused about making newer detectors and also larger detectors. Again, the problem is if we have 1 kilogram germanium detectors, we're going to need 1,000 germanium detectors with the associated electronics chain, and that increases the background, and that increases the cost considerably. So what we are doing is we're doing research in order to have much larger masses. We're working with the vendors, and this is a 17.5 centimeters is almost a 7 kilogram germanium crystal. So what we're trying to do is see whether we can reach, and if we do that, of course the reduction goes directly with respect to the mass, and that will reduce a lot the again, potential for background and also cost of electronics. So the ideal detector is the source serves as the detector. It's an enriched source to minimize active material. You would prefer to have the case that has the largest Q value, because having a large Q value takes you out of some of the potential backgrounds, the natural backgrounds. So calcium-48, for example, would be ideal. The only problem is that has a Q value of about 4 MeV The only problem is the enrichment of the calcium-48 material would be very costly. This idea about direct identification of the decay progeny in coincidence with the neutrino double beta decay essentially would the decay eliminates all the potential backgrounds, with the exception of the 2 neutrino double beta decay, of course. This is in connection with the barium tagging. If that is successful, that would be very successful, meaning as well efficient. Right now they have done some proof of principle, but the efficiency is low. And essentially there are some issues associated with nuclear theory. There are major sources of determining what would be the half-life. And the bottom line is that there is no one ideal isotope in the experimental technique. In summary, the observation of neutrinos double beta decay would demonstrate lepton number violation and indicate that neutrinos are Majorana particles, constituting a major discovery. It needs to be confirmed from independent experiments and different isotopes. I think at the end we're going to require, if it is observed, it will require other isotopes. If it's observed, then opens an explicit sensitive window to search for physics beyond the standard model. The measurement of this effective mass is complementary to direct and cosmological measurements of neutrino mass, and measurements in different isotopes should also provide insights on the underlying physics process. So this is the legend collaboration. There were 220 scientists from 47 institutions, and thank you very much.
We have time for questions.
Okay. Thank you very much for this general report about the double beta decay. You presented Gerda as your competitor. At least for some years, there were discussions about the merging of the two experiments. Now I realize that there is a new project which is legend for this merging.
Correct.
Is this the situation?
That is the situation. So we're going to be using their cryostat. We're going to be moving our detectors to Gran Sasso. We're going to buy additional material from both from the US and in Europe. The combination of the two, we're going to be using their idea of the active liquid argon, and then the controls on the materials, we're going to adopt the Majorana standards. So essentially what both Gerda and Majorana were roughly 40 kilograms. Gerda moved a little bit faster than Majorana did, and they reached the levels before we did, before Majorana. Eventually, the two of them are basically equivalent, but now we're realizing that we're going to choose the best of the techniques between the two of them. So
yeah, I understand that it's not only the merging of the two, but going to a new project.
Correct. And this is we're trying to these large collaborations. Sometimes they are not that simple to merge, because, for example, the Europeans are used to different project management techniques, and the money, a good chunk of the money is going to come from the US, and the agencies have very specific rules about the project management, which in Europe sometimes we are trying to get some common language about how to collaborate, which is not trivial. Let me put it that way.
Thank you very much. I have a comment.
Yes.
May I make a comment?
Yeah, sure.
We say, this question of the mass sometimes is presented is that there are different methods of measuring the mass, okay? With the triple beta decay, then the double neutrino-less double beta decay, then cosmology. I think, you see, one has to clarify that these are not different methods. These are three experiments that measure different quantities, not the same quantity. In fact, in the case of tritium beta decay, it's an incoherent sum of the different contributions. In your case, you have an if. If neutrinos are Majorana, and the others there is no if. Okay? Here there is an if. If neutrino Majorana, then you have a coherent contribution of them. That means it's a completely, principally completely different quantity. And the only one that is really the sum of different masses and nothing else is cosmology. But then you put a lot of cosmological background that you have to believe. Okay? Which is another.
Again, it would provide consistency or insight in terms of the masses, but I fully agree with you. There are these other experiments we are also somewhat involved on them, like Catherine and on the endpoint of the direct detection of the tritium endpoint. And yes, I fully agree.
Okay. No, just this comment because you see, it's like you are measuring the same quantity. No, you are measuring completely different quantities with these things. Okay, the mass is intervening in all of them. That means the masses are necessary, but not the measurement of the mass.
Want to make a comment related?
Not a comment, but more the question. For the legend, your background expectation, how does it translate into the effective mass operator in beta beta? I somehow missed that.
Right. So we'll have to check the number, but we're talking about 0.1 on 10 millielectron volts.
Okay.
I'll double check, but that's a valid point.
Any other questions?
So I have a kind of comment. So this Legend 1000 should be close to the ultimate germanium detector, right? Because how much is 1,000 kilograms of germanium?
Right.
And the comment is because, yes, the backgrounds and the energy resolution are great, but then you will need to move to xenon or to scintillator detector, right? Whereas you can even go to 1 milli or 0.1 millielectron volts when you go to multi-ton scales, right? But here, it should be close, right? I mean, I don't think that they will be 10 ton.
No, so the question is, at some point, what is, how much money are you going to put in order to search for an answer in a physics project? And people tend to talk about, say, 1 billion as a potential limit of an experiment. Legend, we're talking of the order of 300 million. So
the 1,000 is 300 million.
The 1,000 would be the order of 300 million. All of them are roughly around that. That's the level. So it is almost like forming one other laboratory, like every or a fraction of it. So we started to get into a region that the next level might be on the road. Yes, so that's why we're trying to see whether we have ways of improving in terms of the larger size germanium detectors and so on. Of course, if it is being discovered, then we have to revisit the physics and whether the community is willing to. But as I pointed out, and as you pointed before, this is one of the top priorities in physics right now to try to go this way. And incidentally, shameless announcement, we have two positions, immediate positions for one for CrossFit, one for Legend. And if you know of good experimentalists, you join us. Yeah.
Okay, any other comment or question? Okay, let's thank Alfredo again. We don't have any more announcements today.
Okay, so
No.
Oye, no sé si ¿qué dijimos? 50 más 10, ¿es eso, no? 50 más 10. ¿Sí está bien? Okay, so sit down please and we're gonna start. Okay, so welcome to the afternoon session. We have two talks, so one talk, coffee break, no talk, and we have first talk by Francisco Leanda, and we talk about flavor and guts. Okay. Yeah, thank you for running.
So now I'm gonna talk about how to build gut models with flavor consistently, and that they are predictable and they're not that complex. So we start from the beginning, and we want to know what are we made of. And of course the answer is of lettuce. And Mushun showed us that the standard model was made of like plush toys. So I didn't play with
These are different elementary particles. But
these are the same, but they are different
are the
pictures
same
from other angles. Yeah, so I played with Lego, so I want them to be Legos. So I suppose that the universe is made of these things, and these are different types of Legos, and everything is made of it. Of course, there's also the forces. So in here we have the whole standard model. Of course, the standard model is not just that simple. It's something like this. With all of the information that I wrote in here, you can write the standard model potential, and that it's everything there. And it's the best theory that we have built, but there's a lot of problems with them. We see them as problems, but they are really questions we want to understand. Why? Because it works really well in the end, but we want to understand more of it. First is the hierarchy problem. Why is this? This is the only dimensionful parameter in this table. Why is this so far from the Planck scale? Now charge quantization. The U1 charge can be any number, any real number, but they're all integers if you multiply everything by 6. The next is this strong CP problem. This is 0. This is measured to be 0, but can be anything. Why? 0 is a very special value. Why is it? Now vacuum stability, if we run this, it goes negative, and that's very bad in the standard model. So that's like a cry for this. The standard model does not work all the way. There is no dark matter candidate in here. There is not enough baryon asymmetry. Mushun was talking about that. If we calculate the matter-antimatter asymmetry in the standard model, is way less than it actually is. And furthermore, there's lack of neutrino mass mechanism. There's no explanation of everything in here. So the standard model is, even though this is one of the things that makes it incomplete, everything else I mentioned, it's like, well, we would like to understand more, but this makes it incomplete. Of course, now we want to understand all of these numbers. There's 10 to the minus 5 and a 1 and different angles. There's no reason for that. We want to understand that. And there's a few parameters that we haven't measured, like this one.
I think the zeros you were mentioning, if I understand you correctly, this is a theorem. I mean, that we understand. The zero in the W mu and in the B mu. These are the charge. They have to be zero.
Yes.
By the gauging value.
Yes.
That we understand.
Yes.
Okay.
Yes, that we understand. Yes, of course. And there's a few more that aren't in the table because we don't know much about them. But we want to know about them. We want to solve things. And just as he was saying, there's a theorem. There's something that guides us, that fixes, and that's symmetry. Symmetry has always guided us into making everything simple and making relations between particles. And that's what we want to do. We want to relate all of these by symmetry. Now, I think the best shots at symmetries are listed in here. The gut, which unify this way, flavor symmetries, which unify families, and SUSY, which unify different spins. Extra dimensions can do that too. So these symmetries help us to understand these connections. But how about we make them, all of them go together? We want theories that are extra dimensional guts with SUSY and with flavor. Why? Because we want to collapse, we want to make all of the relations that we can between these particles so that there's not that much freedom and that we can predict their values. So how do we do that? Well, this is a lepton workshop.
Including charge quantization then? No.
Well, of course, charge quantization is explained by guts.
If the group is simple.
Yes, of course.
The unification
yes,
is simple.
I will be only working with SU5 and SO10. So
Okay.
yes, yes.
But then you have to put the condition.
That it is a simple group, of course. So we start focusing on with leptons. As I just said, this is true. These are true problems of the standard model. There's no explanation for this. So the questions are how are neutrino masses generated? Why are they so small? Why are the angles so different from the quark sector? And is there CP violation which can bring us to leptogenesis? So the first point is neutrino masses. How do we generate them? Well, I'm going to list like the simplest mechanism because I am very ambitious. I want to build a gut extra-dimensional SUSY flavor model. So I don't want to start from something complicated from the start. So I start from the simplest thing, and the simplest thing is just add right-handed neutrinos. Therefore, neutrinos have mass through the usual term, as in every other Fermi in the standard model. Again, the simplest thing that I can do is add two right-handed neutrinos, because M1 is still not measured, so it can be 0, and that can be fixed by having just two right-handed neutrinos. Next question. This is the spectrum of the fermion masses in the standard model. If you see there's even though there's a lot of hierarchy between them, there's a lot more in here. And this is too much of a difference. So we want to explain that more important than we want to explain that in here. So this price again for some explanation. And again, the simplest explanation is the CISO. The simplest of the CISOs is type 1 CISO, which is having the right-handed neutrinos with a Majorana mass, which is very large. The masses go like this, and since this one is inverse, the mass this is very large, this is inverse, this one is very small. That's a really simple mechanism. So again, now we're extending the standard model with right-handed neutrinos and type 1 CISO. The next question is mixing angles. We saw this image earlier, and we want to understand why is this almost diagonal and why is this almost full everywhere. Well, since this is almost diagonal, there's like again, I just said it's almost diagonal, so there's not much info there. But here it isn't diagonal. It's everywhere, big numbers everywhere. So I want to understand the symmetry in here. And the first attempt, and everybody talks about, is the driver maximum. If you look at it, these two are kind of the same and very big, so it's kind of like half. These three are kind of the same, so it's about one third. And of course, there's a 0 in here, and we know there's not a 0 in there, but this is so beautiful, I'm going to work upon it, because there is so much symmetry in the drive-by maximum that we want to see the ideas that work behind it and make them work. So how do we obtain the drive-by maximum? The drive-by maximum must be obtained by us flavor symmetry, which is broken somehow. There must be a new field that breaks this flavor symmetry G. These new fields are called flavors. The simplest way to do this is making the leptons a triplet, the flavons an anti-triplet, and right-handed neutrinos and Higgses a singlet. So the masses, the neutrino mass, the direct neutrino mass, the structure of the mass is controlled by the bed of these flavons. So the web of these flavons is how the flavor symmetry breaks. So exactly the breaking of the symmetry of the flavor symmetry determines the mass matrix of the neutrino. Well, this is a nice idea. The minimal, again, is having two right-handed neutrinos, so the minimal is having two flavors in this set. And this is something which I really like in the drive-by maximum. The two flavors that we need to obtain the drive-by maximum have this alignment: a 111, a 011, a 001. This is an extra. It doesn't add to the mixing angles, but this allows the third right-handed neutrino, and it fixes its mass. If we don't have this, then the lightest neutrino has a mass of 0. But you see this kind of triangle, it's really, really, really highly symmetrical. That's why we keep talking about the triangle maximus, even though we know it is wrong. We want to keep talking about it because, well, symmetry. There's no other reason. We love symmetry. But again, triangle maximus doesn't work. So what should we do? I already made all of the setup with the type 1 CISO, with some right-handed neutrinos. That's the simplest mechanism that I can do to give neutrino masses and to have some flavor structure. So what I do is I start looking for different flavors. And how do I do that? Well, this one was done by Steve and his students. Just find alignments that work with integer entries with no faces, and that's just plug in numbers and see what they give us. Interestingly enough, these alignments for the flavors work really, really well for N1, 2, 3, and 4. For N1, this is the trivial maximum, because N1 is 1, 1 minus 1, and we can always multiply by 1 minus in the end. So this is like the continuation from which the trivial maximal alignment comes from. The first one, we know it doesn't work. The second one works really, really well. The third one works really, really well. And the fourth one works kind of okay. But this was found just plugging numbers. No symmetry involved. I just want to know what alignments work. But is it really that nice? So let's see the minimal setup. Just what I have said. The neutrinos in CSD3, that means this is called constraint sequential dominance. The name is not important. Just I'm going to refer it as CSD. N equals 2 or 3. Those are the ones that I'm going to work. I'm going to write the example of CSD3. That means N3, that's 1, 3, 1. And this is the usual flavor that we already have. So the neutrino masses are going to look like this. I'm going to have the minimum setup, so type 1 CISO, 2 right-handed neutrinos, diagonal charge leptons, so charge leptons do not add anything. And the only physical phase here, I'm going to fix it to minus 2 pi over 3. This is fixing the model. There's no mechanism to fix it. I just want to show how good this works. So there are only 2 real parameters. And this is going to give me the whole PMNS, the neutrino mass differences. So, of course, there's a diagonal charge lepton matrix which gives the charge lepton masses. So there are in total 3 masses from here, which one is 0, the 2 mass differences, 3 parameters, 4 from the PMNS, so that's 7, and 2 Majorana masses. So that's 9 parameters out of 2. How good does this work? Well, this is the latest experimental values, and this is what the model makes. So as you can see, there's a chi-squared of 3, so that means in total, if you assume that the total deviation is just 3 sigmas away, so this is very, very close. And this is actually impressively close, because it is really rare to obtain a model that gives us these experimental values. Furthermore, these are the 2 A and B, the A and B that I need to fit in here. These are the 2 values that I must give. And it is again something curious that one must be exactly 10 times the other. I didn't put it in, it was just a fit. So this is impressively predictive. So there are 2 parameters for 9. And so close to the current experimental values. These are this year's values. So this is really, really close. So I want to build a model that can be as predictive as this that I'm doing. Furthermore, as I just said, there's CP violation. That's the last question that I.
But the contribution is almost the same because you have a 9 there, and on the other matrix you have 1. So basically, A times 1 and B times 9 is more or less the same.
Yes. Yes.
So the entry is more or less the biggest entry in one matrix, and the other is basically the same.
Basically the same, exactly. Yeah.
And this is S4, right?
This is
the group. The flavor group
symmetry group?
S4.
We work with S4, which is the most...
Because you need a doublet. So.
Yes, of course. But no, I don't need a doublet. That's all triplets.
You have two right-handed neutrinos.
Yes, there's triplets. So
How?
the lepton is a triplet.
But the right-handed
triplet
are singlets.
and singlets. Yeah. So this we made this with A4, S4, and delta 27.
So do you have a vacuum alignment mechanism?
Yes,
that give you
that's
that?
what I'm going to
Show
talk
it,
about.
okay.
Yes, of course. That's the usual, the main question about the fluid. So this is too good to be true if we don't have a vacuum alignment mechanism. So next thing I want to point out is there is CP violation in here. It is fixed by some symmetry in the model to be minus 2 pi over 3. And that's really good to have CP violation in the leptons. Why? Because if I have CP violation in the leptons, and then I have very massive right-handed neutrinos, then the right-handed neutrinos can decay, violating CP. That creates a difference in between leptons and anti-leptons. Then this difference becomes baryon. This lepton asymmetry becomes baryon asymmetry through spalioness. So I can explain the antimatter-matter asymmetry of the universe thanks to this phase, which is called the leptogenesis phase. So this is like a kind of dominoes falling because it's a complex process. The first thing in this model is that the CP violating the Lepton phase, if it's more than 180 degrees, then there is a possibility of baryon asymmetry. We can calculate this. So, and of course, the measured value of the electronic phase is more than 180 degrees. That predicts a positive difference, which is what we are. We are more matter. There are more matter than antimatter. And if we want the exact value of the baryon asymmetry, the lightest right-handed neutrino must be about 10 to the 10 GeVs, which is compatible with SE5 theories. And we can do N2 leptogenesis, which is the second right-handed neutrino, the second lightest. That works really well with SO10. So this alignment, it explains predicts the 9 flavor observables in the neutrino sector, and together with these masses for the right-handed neutrinos, it predicts the correct baryon asymmetry of the universe.
Let me understand this point. This relative phase that you have.
Yes.
Is in the high energy scale.
Yes.
Okay? That means the Majorana sector of the theory of the heavy particles.
Yes.
You have 3 families, in principle you have 2 phases.
Yes.
Okay? For the Majorana sector, I don't mean for the present active neutrinos, low energy. But in that case you have 2. What happened with the other phase?
So the neutrino mass matrix is this one. So I can absorb this phase and put it in here. So there's only one observable phase in this structure.
What I mean is that there could be, you see, with 3 families, you have a basis of 2 different matrices. There should be a third one with the relative phase, is what I'm saying. Yeah, in principle, you see, these 2 terms could be understood like 2 bases with definite phases. For the complete matrix.
Yes, but there is only one observable from in here. If I were to have the third matrix, of course there would be 2 phases, but I don't have 0. So, what can we conclude? This alignment, this is the first idea that I want to tell you, that this alignment is astonishingly good. It brings the 9 parameters in the neutrino sector from 2. Furthermore, with 1 extra parameter, I can predict the baryon asymmetry of the universe. But my talk said that this is about cuts, and I'm just talking about neutrinos because this is the main focus of not only the workshop but the symmetry. We just start from the BMNS. Everything starts from there. So everything I talk is very easily put into an SE5 here. I'm not going to talk about it because I want to talk about the hard stuff, making it work with SO10. So if I want to make a God-compatible theory, we need 3 neutrinos because I'm thinking in terms of SO10, so there's 3 right-handed neutrinos. So I'm going to add this matrix, of course, in here, since I have this 3 matrix, now there are 2 phases.
This is what I was saying.
Yes.
In principle, you have to have 3 terms and 2 relative.
When I have 3 right-handed neutrinos, there are 2 relative.
Now I'm happy.
Yeah, okay. Now, this is usually expected to be really small. In a few slides, I'm going to explain why. So this is not going to contribute much to the PMNS. Furthermore, it's only on the 3P entry. So this doesn't change all of the results that we have. But it does, it helps us to make M1 different from 0. And in here, this phase was fixed to be minus 2 pi over 3 in our previous slides. Now I'm leaving them free just so that we can count the amount of parameters that we have. So if I have, in the end what I want is to have this CSD3 alignment. This alignment works really well for the left-handed masses, Majorana masses. Curiously, if I have the neutrino masses in this alignment and the right-handed neutrino masses in this alignment, then after the CISO, I get this alignment again. So that's one result that we proved in here. So when you have the structure from two flavons, the mass matrix is from two flavons, the same one in the Dirac mass, in the right-handed neutrino mass, then you get the same structure for the left-handed mass. That's really nice because that is what we want in unification. We want like bring everything to be kind of the same. And now in unification I can't make the right-handed, the charged leptons diagonal, and these have this structure. I have to have something similar. So what I do is I have this structure. This comes twice the phi 1, twice the phi 2, twice the phi 3. There's only one difference. In here, instead of phi 1, I get phi 1, phi 2. I don't want to bore you with details. I just want to show that this is a slightly different from this. These are the same phases. This is fixed from the model. The phase in here must be the same in here. This is bound to be small because after the CISO, this is divided by the third right-handed neutrino, the heaviest one. So this is going to be fairly small. It's not going to affect the parameters that I showed you before. But this is needed if M1 is different from 0. So this, in the end, is going to fit M1 different from 0. Even if I run these phases through all of the 200 and the 360 degrees, they don't change much, the angles in the PMNs. They're not that important. They change about 5% in the PMNs. However, I was about 5% in the chi-square. With all of the parameters, I was about 5% from the exact center point. So with these phases, I can make my chi-squared exactly zero. So what can I do with this? With this structure, I can get a perfect fit for all of the observables. It is 12 flavor observables. We have, if I count from here, there are 8 real parameters. 3 of them are kind of negligible, but they are there. I have to count them. So this is quite predictive. Even though there are a lot of new parameters, this is predictive. But I talked about God compatible things. So the quark sector must be in the same structure if I want this to work with a true God. So what happens if I propose exactly the same structure for the up quarks and down quarks? Well, this is again the same structure. This is a mixed term, 1, 2. This is 1, 1. We want this because this texture series is really important for us. So, this is the same structure for leptons and for quarks. This is rarely done because it never works. Again, the same phases in here. And now this is not small by all means. This is a top mass. We do the fit, but there's one difference from the leptons than quarks. Leptons must also be run to the God scale. I cannot fit the low energy parameters. I have to fit everything at the God scale. But with quarks, the SUSY threshold corrections are very important. While in leptons, they are important, but they don't change much. They are naturally small. So I'm going to add these parameters. These SUSY threshold corrections can be parameterized in 2 parameters, in 2 numbers. So I'm going to add them to the fit. So there are, again, 8 free parameters and 2 SUSY threshold corrections, and I can get a perfect fit through the box. I know that really sounds but that's impressively hard to do. That's really, really hard to get a good fit for the quarks. There's 10 parameters for 10 observables. I'm not predicting anything, but I'm doing this in a gut structure. So if you see, there are only two kinds of matrices, one for the up-type fermions and one for the down-type fermions. So this is quite an achievement in itself. I'm just showing you that this alignment not only works for leptons, but it works for quarks. So it is predicted in the lepton sector, and it is one-to-one in the quark sector. This is highly symmetrical. This is nice even to look at. I like this. I'm talking about the CSD3, but I told you that it was a series, so everything, absolutely everything applies if I work with CSD2. So this is another alignment. The mass matrices just changed this. So what have I shown you is that there is some alignment that is kind of what we did with the tribal maximum, but different because the tribal maximum is wrong, and it works. It works perfectly for the leptons, and it works really nice for the quarks. That's really, really rare. So I can build an SO10 theory with this, and I have. So this is the theory that the models that we have built, trying to be more and more and more simple. And of course, there lies the questions that Mushu was asking. How I gave you this alignment, but that's like cheating if I just say this is the alignment and there's no different than just fitting numbers if I don't tell you where does CSDN come from. So the flavors, these are the CSDN alignments that I want. This is the usual. There's a sign because everything is, if I multiply everything in the third energy by -1, I get the usual thing. This I know how to get, but these two are the weird ones that I need to give you an explanation of why do they exist. And the answer, the simplest answer, is S4. If you see, we have explained it with A4, SU3, S4, and delta 27. The simplest of them is S4. Why S4? Because in S4 I can write the generators in this basis, and the generator SU, multiplying this by this, leaves the invariant, the belts that leave this SU invariant have this structure. And all of the flavons, except the 001, have this structure, the ones that I mentioned. So I want to work from S4, because in S4, theoretically, it is easier to get these alignments. So if I choose B equal, well, that's not important to detail. But all of them are eigenvalues of these SU matrix. So what do I do? Of course, I write an alignment potential. And an alignment potential is a superpotential where I get the F-term equation, so this means that when I divide by over x3 prime, and this gives me an equation, and I solve it, and each term. This is a really nice trick to do, and I'm going to explain term by term. Of course not, I'm not going to. This is really ugly. This is even the best, the simplest superpotential that we have obtained to align the flavons in the structure that we have. This is really complicated, and even though we have to do it, I don't think anybody would believe that nature has this alignment potential.
I have a principal question about this kind of thing. So, I mean, for example, you talked about A4 and S4. A4 is a subgroup of S4.
Yes.
Does that mean that S4 is the same as A4 just with some parameter fixed, or is it a completely different model because you have different Higgs fields and different other assumptions?
No, well, there's simple. So the difference between here you see the generators of S4. So if you keep S and T in this way, this is A4. If you don't include Q, right? So that changes the way that the flavons connect with each other. It changes the symmetry overall. There's not a one-to-one relation with parameters.
Well, as a subgroup, I could imagine that just adding the generator I just get an extra relation. That's one way of doing it. Another way of doing it is to set up a completely different model where I now have new fields that transform non-trivially under U, and then it's a completely different model.
That way of thinking is not completely correct, because, for example, in S4 you have doublets, and in A4 you don't have doublets.
Well, the question is, what do you use?
What I use?
Yeah, I mean, you have doublets.
Yeah, no, I
you don't have, you have or you don't have. But if you set up a model, you make choices, right?
Yes, yes.
And my question is, if you go from A4 to S4, are you simply just constraining more parameters, or are you introducing new fields with new transformation, with different transformation parameters than the other model?
Yes, I'm introducing different transformations. So we can conclude that even though this works and this gives me the alignment that I want, we don't believe this is how nature works. It could be really ugly, because everything I am predicting with the Fermion masses, I'm losing in this ugly thing. So do we have some other mechanism to align flavors? And now I'm going for something completely different. I'm going to digress slightly into guts.
But I have a related question. I mean, how important are these flavor groups for you? Because I mean, it seems you take A4, you get some fit. You take S4, you get some fit. You take delta 27, you get some fit. So is there anything which you can rule out? So is there a group which doesn't work? It seems like you take something and put some parameters and some flavors, and then you have to model.
So the way that we build models, yeah, we don't rule out anything. Yeah, I can just choose the group. What changes is how simply can I get these alignments.
But then, I mean, these predictions are not really specific to our group.
No,
so you just have a group.
They're specific to the alignment, not to the group.
And the alignment is something which you sort of put in by hand.
Up to now, yes. And I of course, this is a mechanism, but...
No, I'm just asking, it's not criticism,
yes.
but I just ask.
Every time we build a model, we'll give the alignment mechanism. But what I want to show you is, this is the usual way that flavors are aligned. Now, almost everybody does that. Some alignment mechanism, alignment potential.
But this is, you have the so-called driving fields.
Yes.
Which they are called, but they are just Lagrange multipliers.
Yes, they are.
So it's like, it's as good as saying I have this ref because I want it.
Yes, kind of like, yes. That's the whole point. But I'm going to show you another mechanism that does not involve that. That's the whole point of the talk. So I just want to go into guts, because yeah, when one sees one flavor alignment, immediately one asks, how did you get that? But when one gives a bed that breaks the guts, nobody asks, how did you get that? Even if you have, in SU5 you need an adjoint, a 24, and of course you have to drive it, but the 24 can get two directions. The one that breaks into the standard model and that one that breaks into SU4. And we always ignore the SU4 one and take the good one. But that's an alignment. We need a mechanism to align the guts. Not just guts, in two Higgs mechanisms. The first, if I have one Higgs, there's only one bed that it can get, that breaks SU2 into U1. If I have two Higgses, it can have this bed. Of course, we ignore this A because it breaks electromagnetism and we don't want, but we ignore it. There is no mechanism fixing it to be zero. We choose sometimes and or sometimes not to have this phase. But again, this is choices. There is no alignment mechanism for that. There is no alignment mechanism for what I just said. In a 24 can break into the standard model or SU4. We always choose this one because that's the good one. But in the model, it could be this one. In SO10, the things get worse because the 16 can only break this. That's really nice. But the 45 can break in any of these directions and break color and break the SU2 left. But why? I've never ever had, obviously the question of how do we get this alignment is going to come up. But I've never heard someone asking, why in guts do I have this alignment? And the truth is that in 4 dimensions there is no answer. But there is one answer, extra dimension. In extra dimensions I can align the verbs of the adjoints to the one to anything that I want. So I'm going to work with 6 dimensions because that's the structure that I want. So the 6 dimensions are a torus. So usually one thinks in a little square and you paste both ends and you get a torus. The gauge fields are going to travel through the whole torus. One important thing is that when I do this pasting, there's another symmetry that I want to impose, which is a set 2 symmetry, which is I before I do this pasting, I grab my space-time vector dimensional sheet and I paste these points. That means that this point and this point is exactly the same. So instead of having this square, I have like a triangle from the start. There's something interesting that there are 4 points which are identified by themselves, which are usually called the 4D branes. These are branes where fermions usually live there. But the important thing is that there are boundary conditions that I have to put in these points, and everything that lives in the bulk must comply with those boundary conditions. So a boundary condition is any field that lives in here. When I paste around this point, it has to satisfy some condition. And this condition is one matrix that squared is the identity because it's set 2, and it must belong to the symmetry of the group. It can be a gauge transformation or a flavor transformation. And this is where it's done in GAUSS. Nobody says that this is the alignment of the webs, because when you have these conditions, you need webs. GAUSS is broken by these conditions. But if I were to have 24 with this condition, the web that breaks into SU4 is not allowed, because it does not satisfy this condition. Only the web that breaks into the standard model is allowed. So if I have these two conditions...
Why is the web not allowed which breaks to SU4?
So imagine SU4 is SU5 is in here.
You just need another -1.
Just have a different boundary condition.
Just have one more -1 of the diagonal.
Yes, of course, but but if I choose this boundary condition, then I cannot have that web. I cannot have the web that breaks into SU4. So if I had a -1, then I cannot have the web that breaks into the standard model. I'm fixing the web through the boundary condition.
But I mean, you say that you want to break to the standard model, and so you do. But there's nothing which a priori would prevent you from breaking to SU4.
If I have this boundary condition?
So what dynamics is there that prefer one set of boundary conditions?
No, I'm choosing the boundary condition. So indeed, I'm translating the choice of the web to the choice of boundary conditions. Yes, that's true.
Yes, but but it's in principle the same problem as in spontaneous breaking. There you have two different choices of relative number parameters.
I think this is kind of more honest, because you have to make this choice, and in the other problem you don't have to make the choice. You can have the general web.
But there are only two non-trivial possibilities.
Yes.
For the adjoint web, either it breaks to the standard model or SU4.
Yes.
And here it's basically the same.
Of course, in SU5 there are only two possibilities, but in SO10 no, there's a lot of possibilities.
Sure.
So that's why I'm using the SU5 as an example, because it's simpler to understand. But in SO10, this does not allow to break the standard model. I cannot have a web that breaks the standard model.
Well, not with a Z2, yes, but with a higher set, yes.
Yeah, not with this, yes.
But maybe another point is that with the usual for the vacuum alignment, you need a lot of additional fields and additional coupling constants.
Yes.
Where the orbital boundary condition is a cleaner way to do it.
Yes, yes. And
I mean, I also like this much more than the 40.
Yes, of course. If you have SO10, you have to have 116 and 45, so at least 61 fields more. And here it's just a condition. So the whole idea is that this is really nice. So why don't we usually use these boundary conditions to align flavors? So what can the extra dimensions tell us about flavor? So first, there's also the question, again, almost nobody asks, why SO10, why SU5? But everybody asks, why S4? How does it come from an SU3? How does it come from a gauge symmetry? So, can we ask two extra dimensions to give us an explanation of why S4? And the answer is yes. So, I have, again, my extra dimensional sheet, and I paste these points, because that's the set 2. I'm left with a triangle. Of course, the triangle has these 4 branes, invariant branes, which are the center of using the orbifolding. And these branes have some symmetry. I can relate, there are symmetry transformations that leave the branes invariant. And if you see from this diagram, it is really easy to relate that if I fold this, I get the tetrahedron. And the tetrahedron is A4 symmetry. So I can get A4 symmetry without imposing it from the beginning, but as a remnant symmetry of the orbifold. But I want S4. And what is S4? The symmetry of a cube. Instead of the tetrahedron, I want the symmetry of a cube. That's really simple to get too. If I paste dimension by dimension, here the relation was both dimensions negative pasted. If I paste each independently, x5 with minus x5 and x6 with minus x6, I get the same tetrahedron that I got from before and the reflected. And of course, if I put them this way and I connect all of the points, I get a cube. So one tetrahedron and the inverse and the inverted one, I can get a cube. So this is a proof by origami on how to get S4 from the extra dimensions. So extra dimensions are really, really nice because now they have given me some utility. I don't have to put S4 by hand. I can take it from the extra dimensions, from the space-time itself. Now, the real question from the start was, why CSDN? How can I get CSDN? I don't like the alignment potential. It's really, really ugly. Can I do boundary conditions to get CSDN? And the answer is yes. Again, I get independent reflection of x5 and x6. That means, again, we have these four for the brains, but these brains are usually ignored. They are never used because that's the brain that just one reflection leaves. If I just focus on this x5 reflection, there's a 5-dimensional space-time left. This has two brains, two fixed points, which are 5-dimensional brains. So there are like these are places that I can also put fields on. The 4D brains, the bulk, and these new 5-dimensional brains. And what is usually done, the fermions leaving the 4-dimensional brains because I don't want them to comply with any boundary conditions. The flavons leaving some 5-dimensional brains. The brains have lines that connect one 4D brain to another. So these flavons will fill some boundary conditions, but not all. And the Higgs and gauge fields are located in the whole bulk, which fill all boundary conditions. So what do I have? The flavons are going to be located in some lines, which are written like this, but that's much nicer to look at like this. So this is the triangle that I have been talking. This is the extra dimensions. The brains are these points, and the flavons live in the lines that connect these points. These are the 5-dimensional brains that leave one of the set 2 invariant. So what can I do if I do this? Well, of course, I have to impose some boundary conditions in each brain. And for example, phi 1 is going to fill this and this boundary condition, but it's not going to fill this. So it doesn't have to comply with it. So what can I do? Well, I can choose the boundary conditions to be this one. If you remember, the CSDN flavons were invariant under SU. These matrices are the ones that one usually uses. One that kills the first entry, the one that kills the second entry, and this relates the first one to the third one with a negative sign. So, can we do that? Yes. I can just choose 3 boundary conditions, and that fixes the CSD3 alignment exactly. I'm just going to do it really fast. So the first one.
Can you? So are these abelian or non-abelian boundary conditions?
Not non-abelian boundary conditions.
And you don't run into any problems?
No, that has some implications, yes, because that means that the phase is path dependent. That's kind of like the Aramov bomb effect. The phase that the flavors that live in the bulk obtain is path dependent. It's not the usual thing to do, but it can be done.
Okay.
So by doing this, for example, the phi 1, which was the complicated one, this 131, it connects to P0, which is SU, which has this connection. It connects with π1/2, which relates the first and last entry, which is A equals to minus minus 2a minus b, and that gives me the 1, 3 minus 1. So I can do this with all of the boundary conditions. So in the end, by simple boundary conditions, I can get these weird vacuum alignments that I previously shown that they were really nice. So this is the main thing of the talk. That of course there's the superpotential alignment. I can do that. That's really complicated. That makes it to use this alignment not worth it. But if I have these alignments with boundary conditions, I can use them. That's really nice. Of course, if you wouldn't want to use these 5-dimensional branes, you can go into higher dimensions and get separate tori for each flavor. But this is the minimal thing to do. And what can we do with it? Well, we can again build the world with levels. And just to show, I don't like to show tables, but I can build a model with SUSY, with 6 dimensions, with flavor symmetry, which I have chosen to be SU3, with SU10, which is with the dot symmetry. And the main thing that I just want to show is that this is a complete model. This is a complete model that does everything that you want in a dot theory. It has fermions and the flavons, the 2 Higgses, right-handed Majorana masses. There's the difference between charged leptons and down quarks, and the breaking, the H symmetry breaking, doublet splitting. Doublet splitting is something that usually is ignored. When in SO10, here we have 4 doublets, and if you want the MSSM, you have to do away with 2 and keep 2. This is easily done with extra dimension. It is hard to do in 4 dimensions. And we do the Bev alignment with extra dimensions. So I think this is a really complete model, which is predictive, and if I'm not wrong, this is the first GOT flavor model where the table is smaller than the MSSM. Usually when you build a GOT flavor model, the table is huge. You can have 150 fields really easily. If you count these multiplets, there are less multiplets than the MSSM. And that's all.
Questions? Maybe some.
I have a question about SUSY. I mean, how much SUSY do you have in the upstairs theory, and how do you retain n equals 1 supersymmetry in the downstairs theory?
So you made sure that you don't break SUSY in the end. You want to keep the MSSM.
No, sure, but you also don't. I mean, if you just do a naive compact clarification of 2 extra dimensions, you get n equals 2 SUSY at least.
Yes, but the set 2 breaks.
But you have now these 2 C2s which somehow seem not to preserve SUSY.
Yes. Yeah.
I mean, it's somehow surprising that there is any SUSY which survives.
Yes, of course. The way that I use this set 2 times set 2 to emphasize the branes, but the way that they work, they don't break the extended SUSY. I know that they usually, when you have more than 1 set 2, you don't get SUSY at all in the end, but it remains. I don't know how to write it simply, but it is easy to see that yes, there's n equal 1 SUSY remaining.
But the flavors would still come in hypermultiplets because they are living on these branes?
Yeah, they live on these 5-dimensional branes. We write them as these, which are just 6-dimensional super fields with 1 constraint. So they would be a super multiplet. Yeah, they would be written as a super multiplet.
Hypermultiplet or chiral multiplet?
Chiral.
But how so they live? I mean, they live in a full dimension. I don't see any boundary conditions. You just make one of these 2 dimensions very small. Then I have an effective 5-dimensional model, and these are bulk fields.
Yes.
How can they be chiral?
These are chiral 6D dimensions, and the remaining these are chiral 4 dimensions.
No, but the 6D chirality is not 4D chirality.
No, it is not. But when you take out the ones that do not have 0 modes, and the only 0 modes that you have are 4D chirality. Yeah, we have to. Well, this is the main thing of the talk because this is what we work on.
More questions? Let's see, I have time for some.
No.
I think it's a good ingenuity to put all the open problems, great families, unification, at the same scale. The problem from the future of particle physics is that up to there is a complete desert.
Yes.
Unless, and this is my question, okay, first is the comment, not the question. Unless the running of the different components in Playboy or in the symmetry between boards and leptons and things like that, they run at different scales, if you want, with different weights.
Yeah.
That means that
There is something
in this desert there will be some oasis, if you want. Okay? What is your comment?
We are some desert. We would like that there be something, but if you start saying about the desert, everything gets very complicated and you can do anything you want, absolutely anything you want. Whatever you put in the oasis will change everything at the scale. So we assume the desert because in some way, even though experimentally it's not what we want, I think it's more honest to not put everything that we want in between so that the masses and the mixing is pointing to the point that we want.
More questions? No? So if not, let's go again.
Yeah, I have a brief announcement. Okay, so it's a very brief announcement on a prestigious prize that the Mexican Physical Society awards the medal of the Division of Particles and Fields. And this year they have met already and they took a decision. Just to get a flavor of what it is, what it means to us, this award, this medal, has been given previously to distinguished researchers such as Leon Lederman and James Cronin. And now, this year, they met and they decided to give this prize to one of our dearest colleagues, to a friend, in words of one of our, Matthias Moreno, our favorite German, Jens Serlet, for his great contributions on the development of particle physics in Mexico, and particularly his international leadership on electroweak precision data analysis. So, congratulations, Jens Serlet. Thank you very much for sharing your talent and your friendship and all the evenings discussing physics sometimes.
Well, let me just thank you, and I know there are a lot of people here that supported me for this.
Uno de los señores del centro. Ah, el fotógrafo. Ah, no, Ernesto. Sí, se le pasa. Sí.
Are we all here? Okay, so this is the last session of the day, and we started with gases. We talk about coherent, which is coherent scattering is really no, it's kind of fashionable right now. So thank you.
Thank you to the organizers for this nice workshop. This is the third edition of this workshop, and I was very close to the organization in the first one, so I'm quite fond of this event. And I will be talking about coherent elastic neutrino nucleus scattering, and for short I will pronounce it SEVENS. Imagine that this is a Greek letter, and it's always annoying to have Greek letters between, so it's advisable to say SEVENS, also because when we have a N, it's also can be understood as nucleon, and it's not. And also I will tell you about the importance of having the E explicitly there, and for short I will pronounce it SEVENS. Okay? And before starting, maybe I should also say what is not SEVENS. This can be sometimes confused with the coherent pion production, that is a high energy process. Well, this is not. This is a low energy process, and actually the low energy is a requirement for this to happen. And I will intend to give a short review about this process, and I want to convince you that this is a very exciting topic to work on. And of course it will be a very biased review and incomplete because it will be from my point of view, and I will emphasize some phenomenological works that I have done about things that can be done in future reactor experiments that are aiming to measure cells. Okay, and I will continue. This slide is to introduce myself, and I like to think of me as a phenomenologist of neutrino physics turned into a dark matter hunter. Now I'm working here at IFUNAM in the neutrinos and dark matter lab. I'm lucky to work in this research group. Some of them are here, and we're working in these snow lab experiments. I particularly will be working on DEEP, and the PI is the chair of this meeting, and my funding agency is the GCRF, and I will not be talking about the things that are going to be happening in this group, but maybe I will mention one of the projects that is actually related to cells, and that's very exciting. And Snow Lab is in Canada. I was going to say a joke about Canada, but I will skip that or not. Okay, never mind. And well, this is the outline of the talk. I will mention the history of sevens and why is this so exciting. It was proposed in the more than 40 years ago, and this is a standard model prediction. And the good thing about it is that it was measured for the first time last summer at the SNS, and tomorrow we will have a very nice talk about it. And for the perspectives of sevens with neutrinos from reactors, I will mention just some examples of things that can be worked out with this, like standard model precision physics. The weak mixing angle at low energies has not been measured with the precision that we know it at higher energies. And for the beyond standard model, one can study this NSI formalism. One can also study electromagnetic properties of neutrinos that are very important, like the effective neutrino magnetic moment. And also, because it's a flavor-independent reaction, SRI neutrinos can be studied at short wavelengths.
Stella, only question of semantics. If you say coherent, then necessarily is elastic. If you say elastic, it's not true. Okay? You have to say coherent. But once you say coherence has to be elastic. It's not necessary to put both names, yeah. You put coherent.
Yeah, I prefer to put the E in between just to make a difference.
You could say elastic coherent neutrinos, then it's different, okay?
Right.
Yeah.
Right.
But once you say coherent, it has to be elastic.
Okay. This is to make an emphasis that the nucleus is not altered in the reaction.
Yeah, but if it's broken, cannot be. If it's broken, the nucleus, then cannot be coherent.
Yeah, and the nucleus is not also in an excited state and doesn't emit a pi. Okay. Yeah. I will continue. Well, this process was predicted by Dan Friedman from Fermilab shortly after the discovery of neutral currents. You can see in the background, this nice picture is actually the discovery of neutral currents in 1973. And the next year, Dan Friedman put out his nice paper where he said that just like happens with electrons scattering nucleus, there can be the same kind of coherency for neutrinos that have very low energies compared to the size of the nucleus. In that case, the wavelength of the neutrino is so big that it sees the nucleus as a whole and is not interacting with the quarks in the nucleus, but with the nucleus itself. And he qualified his proposal as an act of hubris. This is an act of extreme arrogance. Why? Well, because of the experimental difficulties of elastic neutrino nucleus scattering. And these difficulties were that the only result you have from this reaction is the tiny recoil of the nucleus, just like we expect from dark matter direct detection experiments. Okay. And was considered an act of hubris also because it's pretty much like trying to hit a bowling ball with a ping pong ball. You can easily do that, but it's very hard to measure how much the bowling ball is moving. And also, it's very difficult because of the backgrounds. And he said it's an act of hubris, and he was right, but it was not impossible, as has the coherent collaboration proved. The only result of the interaction will be the tiny recoil of the nucleus, and also for heavier nuclei, you expect larger cross sections, but also you expect lower recoil energies. You need detectors that are ultra sensitive, but detectors that are ultra sensitive are also ultra sensitive to backgrounds, and that's a problem. And neutrons are bad. They produce nuclear recoils. And also you need a neutrino source that goes with these energies. And the picture in the background is Feynman sketching that he was, it's said that he was doing it while solving equations and at the same time sketching in a men's club the anatomy of the dancers or the street dancers. So I think that's really an act of hubris. But for Feynman that was not impossible, right? But just a reminder of how neutrinos interact with matter at very low energies, and this is the good old inverse beta decay, and has been the golden channel for detecting neutrinos from reactors, and it's also the channel that led to the discovery of neutrinos. And the other one is the charge and neutral currents that at very low energies happen when neutrinos scatter electrons. And this should be wrong because this one is flavor independent. This is the case only of reactor neutrinos, but it's a general case. And what Dan Friedman predicted was this one, where the incoming neutrino with the proper energy scatters the nuclei and produces by the exchange of the Z boson the tiniest nuclear recoil. The experimental proposal for measuring this actually was in the 80s. And a bit of history about this one. It was proposed by Drucker and Stodolsky for coherent neutrino nucleus scattering. And well, this was a detector, relatively light, that suggested the possibility of neutrino observatory. And shortly after this one came the first proposal of detecting WIMPs. So actually the idea of detecting coherently neutrinos preceded the direct detection experiments, and that's very interesting. Actually, none of these proposals ever materialized, but they started, and they had this first idea that led the community to start thinking about new ways and new technologies to detect at low backgrounds, maybe WIMPs. That's very interesting. Well, as I mentioned, we need a neutrino source that is around the 50 MeVs. That is the maximal energy required for the coherent neutrino nucleus scattering. And we happen to have plenty of sources in this region. We have the solar neutrinos, we have reactor antineutrinos, and also if a supernova happens nearby, we would be able to detect it with experiments aiming to detect sevens. Also, sevens has been proposed as an important process in supernova reactions. And as I mentioned, the last decades, the physics community has been pushing towards the detection of WIMPs, and these technologies, the development of these technologies is what actually allowed the first detection of sevens. And as direct detection dark matter experiments are aiming to go to lower and lower sensitivities, at some point they will reach this wall or this floor that is where the solar neutrinos will be an important background for direct detection experiments. And actually, dark matter experiments are also moving towards the possibility of having sensitivity to directions, and that's very important. And some people see sevens as a problem in dark matter experiments, but can also be seen as an opportunity for actually seeing something, and that's very nice. Just as I remember from last week, Jose in his lectures at Simvestab was telling us about Kamiokande. The NDE at Kamiokande is nucleon detector experiments, and they were aiming to detect the proton decay. They never saw that, and at some point there was Kochiba who made an executive decision, and he said, well, we cannot see what we want to see in this experiment, but we can see the background, and we will study the background. And actually, measuring right the background in that experiment led to a Nobel Prize.
When you said that?
You said that in your lectures on physics. I think it was Wednesday.
You were there. You were there.
So I like to think.
This is exactly the same as Koshiba. And Koshiba got the Nobel Prize for studying the background.
Yeah, so that's why I think that it's very, very nice that the detection dark matter experiments can aim for a signal that it's there and they know that there's something there. Well, about the sevens cross-section, it can be calculated from this effective Lagrangian, and when we work out this, we actually get this cross-section. Here, m is the mass of the nucleus. It's proportional to the Fermi constant. In nu, it's the neutrino energy, and T will be the nuclear recoil energy. Here we have the vector and axial contributions to the cross-section and their form factors. For most nucleus, we will only have a vector contribution, and it's very nice that for bigger nucleus you have a larger cross-section, but it's a problem that the maximum recoil energy will be suppressed by the mass. So you are aiming in the experiments to have lower and lower detection thresholds. And if we neglect the axial contribution, the vector form factor will give a suppression at higher energies, And this will be important for SNS neutrinos, more than for reactor neutrinos that are at this level of energy. And also we could make this approximation that it's a very good one, that the recoil energy in the neutron nucleus is much smaller than the neutrino energy.
May I comment about that expression that we put? Really, you have written in terms of Z and N.
That's
and
right,
then
the number of
you see, the fact that is coherent is that the cross section goes quadratic with the number. Okay, but really, what is coherent in a nucleus is really with the mass number, because if you write in terms of A and the difference N minus Z is isobector, and this is already proved and it's not coherent. Okay? I mean, what is important is the term that goes with the square of the sum of Z and N. Okay? This is truly coherent, this part. Okay? But anyway.
Okay, in this approximation,
you distinguish protons and neutrons, and then it's okay. But it's the isoscalar part is the one that is really new, because it doesn't exist for charge currents with interactions.
Okay.
Yeah.
Well, here I want to show the n squared dependency for T much smaller than the nu, and this is what we have. We have the proportionality of the cross section to the weak charge, and that's very important because you are extremely sensitive to small differences in the weak mixing angle. And if you remember what the weak mixing angle is, actually here is a C. If you remember that this is almost 0.25 times 4, it's very close to 1. So in a very good approximation, the cross section is proportional to n squared. And here I wanted to show that the 7th cross section for coherent is several orders of magnitude above the good old inverse beta decay, and also it's much larger than neutrino electron scattering. And if you think about these 2 orders of magnitude difference, you can think in a napkin calculation that for typical neutrino cross sections, like neutrino electron scattering, we have kiloton size detectors. So for this kind of reaction, we could go to smaller and smaller detectors, and that's actually what happened with the coherent collaboration. And I hope to convince you that this 7th reaction is actually a powerful tool in the study of precision, standard model physics, but also opens a whole range of possibilities, like the study of non-standard interactions, the study of sterile neutrinos, or electromagnetic properties of neutrinos. And these smallish detectors also allow the possibility of maybe having reactor monitoring, and also could be a reaction mechanism for the detection of supernova neutrinos. And there's also an important interplay with dark matter direct detection searches, because this will be the background, but in the very far future could be 7s used as calibration for dark matter detectors. Well, I will just say briefly how was this first measurement achieved at the SNS. And this is actually the cesium iodide 14 kilogram detector. They published in Science and made the cover later, and this was also named Breakthrough of the Year 2017. And they had this great idea of 3D printing their data that I like very much. So this is the result. Sorry. Well, this is the likelihood fit to the data in both in photoelectrons and in energy and time scale, because they are sensitive to both, since they have a full spin. And you can see that this is what they measured, the 134 counts. And the standard model prediction is right here, so they are compatible with the standard model prediction within 1 sigma. That's very nice. And they have observed the 7th reaction at 6.7 sigma. Well, this is the SNS facility. They have a pulse proton beam hitting a Mercury target, Hg, I was going to say, target, and they produce pions. The pions decay at rest, and from a two-body decay at rest, you know how is the energy of the mu neutrino. It's just a line. And from the three-body decay of the muon, the form of the spectrum for muon, antineutrinos and electroneutrinos is also very well known. They have different technologies that are being deployed there, but it was with cesium iodide that they made this first observation. And well, this is the counts that the data with the Monte Carlo expectation in photoelectrons or energy and in time. This is also the n-squared dependence for the cesium number, and the black line is for full coherency with the form factor equal to 1, and the green line is for some model of the form factor that at the 50 MEPs at this experiment are very important. And I think the width of the line takes into account the 5% the form factor uncertainties that are at the order of 3 to 5%. And there are many, there is much more to come from coherent collaboration, and we are all looking forward to hear about it. And see tomorrow talk by Alfredo. And now I will move to what are we expecting to see from reactor neutrinos. Okay, there's been since more than a decade ago very important experimental efforts aiming to detect this reaction at reactors. One is in Taiwan, 2 of them are in Russia, the red and the NuGen experiments. Red is two-phase xenon experiment. NuGen, it's germanium, high purity germanium, just like Exono. And here is Conus. It's also a germanium experiment from Germany. And this experiment actually presented results in Neutrino Conference, and they are claiming to see a 2.4 sigma signal within this. So they claim to see the first hint of 7s at reactor neutrinos. And there are also the ricochet and nucleus experiments, I think, in France. Those are volumetric experiments. And in the US, there is the coherent collaboration aiming to see from the spallation neutron source that has been joked about it that the name should be changed to spallation neutrino source. And the minor collaboration, it's a silicon and germanium-based detector at Texas University. And here in Brazil, actually this experiment has contribution from UNAM. There are colleagues from ICN working there, and they are aiming to detect 7s with CCD cameras. It's silicon detectors. They look like this. Oh, and there's very good news from our group that we may be appearing in this map very soon because we're starting a project. It's a collaboration with the US, and I just stole a few slides from Eric, and I will show you some good news. But this is actually a new technology that has been developed for different, not liquid argon, but for CF38, for the PICO experiment that is actually the sequel of Picasso and Cook experiments. And the idea is to use these bubble chamber technologies for very low energy thresholds in a liquid argon to detect sevens for the first time. And this is in collaboration with Northwestern, Fermilab, Drexel, and Indiana. And actually there are students working on the design, and we are planning to use germanium detector here at the lab to screen the materials that would be used there. And this is the phase diagram for the nucleation of the argon or xenon. And also one possibility is to observe sevens, and another one is to look at very low mass dark matter winds. And one very nice possibility to be the measurement of neutrinos here at Laguna Verde. And that will be very important because no one has ever measured neutrinos in Mexico. So neutrinos from reactors, it's what it's next, maybe. And some different technologies are being studied, like the silicon and germanium, or high purity germanium, or noble gas chambers. And here is a list of some of the references for this CONUS proposal that actually observed with the 4 kilogram at 2.4 sigma XS. The Texono collaboration that is deploying also different technologies, and one of them is high purity germanium. And the CONI experiment at Brazil, the RED experiment, and also as Nuchen, it's at the Kalinin power plant near Moscow, and the Mariner experiment, and the Nucleus experiment. And actually, one can think about what these experiments could measure in the future and make a raw estimation about how good precision could we achieve, for example, at the measurement of the weak mixing angle. And this what could make this estimation, but we could also use we could also rescale to the mass that they are aiming to achieve. And for the case of the weak mixing angle, we have this parameter is actually the mixing between the electroweak ion states, and for any renormalization scheme, it's predicted to be this value, of course with the proper rolling.
This is for the on-shell.
For the on-shell. Yeah. And with this, I want to show you how bad it is measured, or how poorly we know this parameter from neutrino reactions. And for accelerator reactions, I mean the low energy LSMD and CHARM experiments from the 90s. And for reactor experiments, here this measurement comes from all the reactor experiments that measure neutrino electron scattering and not via the inverse beta decay, as is in the case of the Texono neutrino electron scattering experiment, MUNU, Krasnoyarsk, and Rovno. And for doing a global fit of this data and taking into account the latest prediction for reactor neutrino fluxes, we get this huge band, okay? That compared with what is expected to improve at low energies, it's actually not that good, right? So there is plenty of room for improvement at low energy with neutrino reactions. And one possibility is at sevens experiments. And if we think about what the xenon-based red experiment, or the silicon-based experiment CONI, or the silicon and germanium-based experiment would be able to measure, we can see that if we assume that there is a 50% statistical error or a global uncertainty in the total number of detected events, we can see that the value could be improved. And if we extrapolate to low energies. And this black curve takes into account the systematic uncertainties that come from the reactor flux. But also we could think of how the systematic uncertainty would change if we want to achieve a percent uncertainty in each experiment. And we will see that for the case of the CONI experiment, we have a different slope because it's the case of silicon. And for these two germanium-based experiments, we expect the same behavior. And this difference is because the ratio of protons to neutrons is higher for silicon than it is for silicon and germanium, or for xenon. And in that case, if we look at what the reactor neutrino experiments with sevens could be able to detect, we see that the measurement will be much better than for neutrino electron scattering, and actually could get in the same level of precision than is expected at the QE experiment, for instance. And now I will move to NSI and neutrino magnetic moment. If we have an effective Lagrangian, we mentioned 5 operators, any new physics interactions that affect neutrinos scattering with quarks could be parametrized with this epsilon non-universal or flavor changing parameters. And this would be any new physics or this model independent way to parametrizing. Anything new could be inside this block. For a nice review, you can see any of these references.
Can I ask a question? So, because of the quarks, but at the end what you have is just is basically the nuclei. So, how do you extrapolate what happens in this case to nuclei? So you have the quarks, then you need to have something else.
Yeah, in coherent neutrino scattering, all the information from the nuclei is inside the form factor that is well known at the 5% level.
But if you have something with like a tensor interaction, it won't be the same form factor for sure. It will be different because you will have spin effects.
Of course, yeah.
So the form factor will be completely different. There will be different form factor, nuclear form factor. Or is it still the same? So you use different nuclear form factors according to the interaction you have here?
I don't know, for a different Lorentz structure?
Yes, but yeah, for different. In that case, you would have different Dirac variables to say, right? You can have like vector, scalar.
But at the order of reactor neutrinos, form factors can be set to 1 because you are at very low energy.
Even if you have something
10 maybe.
Even if you have spin effects, like spin, because if you have something like tensor there, it would need some spin effects. They can all be set to 1, really?
Yeah.
I'm surprised.
But from the plot that I showed before, you need the form factor for the cross section to go to 0 at 50 MeV, but with reactor neutrinos you are working at an average energy of 5 MeV. So
perhaps you are thinking that the effective Lagrangian is written in terms of the quarks. And normally people talk about the nuclear form factor in terms of nucleons, but you have to remember that this is the vector current. And then it's like, you see, the vector couplings of the nucleons, which are not renormalized because of the conserved vector current. There is no problem in writing, you see, for the vector current, the couplings in terms of the force or in terms of the nucleus. In that case, in order to study.
Right, but in that case, this gamma rho is explaining something else that is not.
Yeah, they write it like that, but in the application to, they write in general, it's Lagrangian, but when you apply to coherent scattering, it's only the vector current that is operating.
So I don't understand what would be this non-standard interaction, but what would that mean? Because the way it's written, it means that you have something that is non-standard. Like you can have sigma mu, you can have 1, right?
Yeah, this is for vector axial Lorentz structure, but you could also have different Lorentz structures. Okay, and this NSI could have an effect in the propagation of neutrinos in matter, as has been shown here, and actually the effective oscillation parameters would be affected by this epsilon that contains the non-standard interaction, and this was known as the dark LMA solution here. And another possibility is that it could affect the measurement of or our knowledge of the Dirac phase, the CP violating phase. And for different values of epsilon, you could have different isomorphs here, or or in this by probability plot. And this is expected to be measured at future long baseline experiments. And for the case of for the specific case of sevens, this is how the cross section looks like when we have non-universal NSI. The vector and actual couplings get changed by these parameters that can be also vector and axial, that can go with the U or the D force. And in most of the nucleons, the axial contribution is neglectable. And what is important here is to have different neutron to proton ratio and different detection technologies. Because if you have different targets, you could have different constraints in the parameter space of NSI. This has been shown in some previous works, and actually this came after the coherent result. And this is the constraint on NSI that the last year result of cesium iodide made, and you can see that this constrains the parameter space much more than the experiment charm for mu neutrinos. And we're also working on the sensitivities that can be attained, for instance, for the germanium-based taxon experiment. And the possibility to constrain the non-universal, non-standard interactions parameters is at the order of 10 to the minus 2% for different, assuming different statistical errors or global uncertainties. And this is the case of tensor NSI, where also the form factor was set to 1 for reactor neutrinos. And when we consider different targets, only germanium or a combination of germanium with silicon, we see the slope in this exclusion region is different, and having results from different experiments could be complementary. Another interesting thing to look at sevens is the neutrino magnetic moment. This parameter, this property of neutrinos is expected to be very, very small, at the order of 10 to the minus 19 in the minimal extension of the standard model. But for specific models, could be, for Majorana neutrinos, could predict a larger value of the magnetic moment. Also, the best lab limits we have for this value, comes from neutrino electron scattering, and from the GEMMA experiment in Russia. And we can see from this plot that this is the standard model cross-section, but with higher values of the neutrino magnetic moment, you expect a contribution at very, very low recoil energies. This is at the order of 100 keV, so this is the low energy threshold you want to achieve detectors to be able to exclude the higher values or to have limits that are competitive with astrophysical limits. And this plot is from Texono, also for this germanium-based detector. This is how the contribution from the magnetic effective magnetic moment looks for sevens, and some estimations have been done for future reactor neutrino experiments. And I think there is actually a current limit for the latest result of coherence that can be looked at here. And what one expects from a germanium experiment with these lower energy thresholds from 400 to 100 eV, if we assume a 50% efficiency, one can have sensitivity to the order of 10 to the minus 10. And also this is an example for the case of the xenon-based experiment, red. One could achieve some limits of the order of 10 to the minus 11. And these values are the current limits for neutrino electron scattering at the Texono experiment, at the GEMMA experiment, and from solar neutrinos. Some other electromagnetic properties of neutrinos, like the charge radius, can be probed with coherence. Actually, this is from the latest data released by the coherence experiment. And another interesting thing to look at with sevens is sterile neutrinos. The so-called reactor anomaly, it's this collection of short baseline reactor experiments that after the recalculation of the neutrino flux, one sees that there is a 6% deficit, so where these neutrinos go. So one possibility would be sterile neutrinos. Another possibility is that we don't know well the neutrino fluxes. And this is what we could expect for short baseline sevens experiments. And here plotted is an average probability. And in the blue dots, we assume that there are no sterile neutrinos, but instead that we have a 5% error in the uranium-235 neutrinos. So this could also explain the anomaly, or there could be sterile neutrinos. And actually there are many, and this is the gallium anomaly and the neutrino electron scattering anomaly. And we wanted to see if future sevens experiment could say something about the best fit point of the reactor anomaly. And we can see that for some efficiencies or quenching factors in the Texono experiment, the best fit point of sterile neutrinos could be excluded. This one includes the reactor anomaly and the gallium anomaly. And actually there is a collection of experiments aiming to confirm or to exclude unambiguously, finally, say something about the sterile neutrino. And these are actually some recently has been released data from NEOS, and this exclusion region in the oscillation parameter space has been reduced. And they share something in common, that they all are aiming to study sterile neutrino parameter space via inverse beta decay. So it would be very nice to have an alternative detection method, like could be serums, or actually could also be neutrino electron scattering. And also this is the case of the two-phase xenon red experiment, Russian experiment detector. And we see that even for a 50% efficiency in their detection, and for two different baselines, the best hit point for the sterile neutrinos could be excluded. So they have the possibility to exclude this parameter region. And I will come to an end now. Well, the hardest thing has been achieved last year. That was to have finally a first detection of sevens, and it was done at the SNS. But also there are several proposals that are aiming to study the best hit point of the sterile allowed parameter space. And for this, low energy threshold experiments can reach very good sensitivities, not only to new physics, but also to standard model physics, like is in the case of the weak mixing angle. And I hope I convinced you. I hope that I can show you how this can be a powerful tool in the near future, not only for neutrino physics, but also for nuclear physics. I forgot to mention that from the coherent detection, the neutron radius for the cesium was measured in this model-independent way, and that's an important breakthrough. And also, sevens can have very important implications for dark matter, for technological applications, and that's
more questions are coming to you. Stella?
There is an electromagnetic property, okay, probably it's not so clear that you should put electromagnetic property, which is more spectacular than the neutrino magnetic model, which is that the neutrino has a charge radius in that case. And in the same way that historically, you see, the charge distribution of nuclei and the proton, you see, were studied precisely in the other vertex by electron scattering. Now that you know these parts, then you look in neutrino coherent scattering in the upper vertex, and you can measure the neutrino charge radius, which probably not so far is something that one should look for in that case.
But even the
you agree? That means
still in the
probably we have to talk on this question. Okay, in this neutrino charge radius, which when you talk about that, people open the eyes. Okay?
But I think the proton one is still under debate. You know, we have two definitions. We have a definition, and it's still not known. You know, there's still a debate about the proton charge radius. So maybe first it's to be solved. Comments? Questions? No comments about this? Yeah.
So I'll talk more a little bit about it. Just a comment about the so-called reactor anomaly and this 6% deficit. So the nuclear physics community is also revisiting a lot of the data. So remember, after all, that in the case of the reactor, the antineutrino spectra is composed of something of the order of 800 fission fragments, and each of them has a specific spectrum, beta decay, and a specific contribution of antineutrinos. And a lot of that data is being revisited with the new technologies. People have been using literally tons of sodium iodide in the form of calorimeters, total absorption spectrometers. I think Valencia that's a group that in Europe they have. Oakridge has another one. And the contributions on the upper end in addition to this anomaly, there's something that's called the bump on the spectrum. But the overall value seems to be reduced. So to some extent, it's an anomaly, but it depends with respect to what. And we, what this is making evident is that we have a lack of knowledge also from the point of view of nuclear physics. In the case of the high energy physics, people are more interested in measuring directly than in neutrinos spectra. But I just want to point out that this discrepancy seems to be shortening by the new information coming out from these measurements of only just pure beta decay of some cases.
It's also very interesting how neutrino physics community is moving to actually being nuclear physics. Low energy neutrino physics is nuclear physics.
Well, we're going actually also from the other side, from the nuclear physics.
That's kind of, for the other communities, it's kind of strange to see how people already jump into new things. First you have to check what they see in first, also standard model first, right? But then all these new physics terms and searches is like, okay, we have something new, it's not on the standard model, then you just try something to explain it. So maybe you should just wait to see if they actually go to the standard model.
Yeah, but as you're getting better and better data, you can actually discard some things of new physics.
Yeah.
Well,
and that's good.
If I can make a comment, historically we were talking a little bit earlier about the solar neutrino problem and the fact that this crazy guy Davis for 20 years he does single atom casting 1 mile below, and he crosses his data and he sticks to his guns, and eventually there was an anomaly there and progress was made. So yes, I agree that is important to tackle from the experimental side of things as well. And there's quite a bit of community as well looking into magnetic corrections of beta decay and so on. So theory and also the reactors, 5% of the energy of the reactors is being produced as a form of neutrinos, and this is something that has not been explored at all.
James?
How much might this guy, this measurement of the frequency at the level of cubic was like a 5% measurement, and they had the advantage that it was the protons that was proportional to 1 minus 4 times square theta. But in coherent neutrino scattering, you have that huge n in front of it. So that should make things worse, like at least in automatics. But then I would think for, to get a comparable result, you would have to have like a few per mil absolute cross-section measurement. Is that really what people are talking about, or are these just sort of theory numbers dealing with statistics and not with systematic errors at that level?
Yeah, at this point we cannot say much about systematic errors, but we can think of a pessimistic number, and by that you have a few percent error in the weak mixing angle. And of course this will not be competitive with experiments aiming to do a precision measurement of the weak mixing angle, but I like to think of it as complementary.
But you said it could be like QE, and that would be absolutely outstanding, even though it cannot compete with the Z-fold. But even for that, you would need to control systematics at the per mil level, right? For an absolute measurement. Yeah, that's my question.
I will need to think about it.
Yeah, the neutrino flux and the calibration is a major concern right now, and it's one of the main contributors of the systematic errors, and there is a push for building detectors specifically for that purpose, calibrating neutrinos. So that will be a little bit of the next step. to go to high precision continuum measurements. That's also the idea about doing also differential measurements where you have different distances, different detectors.
More questions?
Like, could you have in the detector energy beams in order to see the origin of the discrepancy in what region of energy of the flux is coming?
For the prospects, for the prospect of all the detectors that you show, yes, some of the technologies they're making emphasis on having the best energy resolution. Because in principle, if it's formed by the sum of all these beta decay processes, in principle the spectra should be bumpy, and we should be able to see that type of information. So yes, we're pushing for the best energy resolution as well. I'll talk more about.
Okay, so I guess we have more detail about coherent experiment tomorrow. You guys no more question about exotic or QV? Okay, let's thank Estela again. So we will convene tomorrow at 9:15. 9:15, sorry. Or you will be aware of schedule.
8:45.
9. Mexican or 9, okay?
So, what are our plans today? Now, do you want to work? Or do you want to go for dinner or somewhere?
Either way, I'm marked.
You're fine.
Any point you're fine.
Maybe dinner, right? 6 p.m.
So that we don't get too late.
That's right. We go the way. I mean, we can go to the mall very soon. There are a couple of restaurants here. I don't remember which one is the best one. But we can just take a look and decide. Yeah, and we might try to choose something that is